Welcome, everybody, and thanks for joining our wolfSSL training webinar today, and for those of you who will also be joining us tomorrow. Intro to myself, my name is Chris Conlon. I'm an engineering manager here at wolfSSL. I've been with the company about 13 years now, based in Bozeman, Montana. If you need to reach out to us as a company, if you have any follow-up questions after the webinar, or are curious about anything, feel free to reach out to us at fax@wolfSSL.com. And, this is our first, virtual webinar training course. So thanks for participating in our inaugural event here. After the webinar, we appreciate any feedback you have as far as things that could be improved or things you'd like to have learned that weren't included. But this is what we're going to kind of have as our objectives for today and tomorrow, is to hopefully give you an understanding of how SSL and TLS work at a protocol level. Learn what the package looks like of wolfSSL after you download the product, how to build wolfSSL for target platforms, some debugging strategies you can use when integrating wolfSSL into your own products. Learn how wolfSSL can be added into an example client or server application. Some best practices for adding wolfSSL to applications and devices, and then just how to learn to use wolfSSL's underlying cryptography library, which is called wolfCrypt. So our intended audience for this webinar is a software engineer or an engineering manager looking to gain an understanding of SSL and TLS and wolfSSL's products. We won't have a lot of hands-on activities for this training course since we're doing it in webinar format. But if you'd like to follow along, and I might have you try out a few things or give you some time to do so here and there throughout the webinar. It is helpful to have kind of a familiarity with C coding and application development. If you are going to be following along and trying some things on your own machine, these are some things that are helpful to have installed to build and run and debug some of our example applications. As far as OS, Linux, Unix, Mac works well with the AutoComp system. You can also do Windows with Visual Studio or Cygwin or MinGW. C compiler, auto tools. Since wolfSSL, most of our products use auto tools with your standard configure, make, install process. A text editor, or something like Vim, Wireshark to capture some protocol traffic, Git to pull down our repositories. We host all of our code on GitHub since we're open source. The wolfSSL products will be helpful to have if you're going to play around with building some of our examples. You'll need the corresponding product to go along with that first. And I'll also be mentioning the OpenSSL command line utility a couple times throughout this webinar to help us inspect some certificates and keys. As far as the structure of our webinar goes, we'll start each day at 10 a.m. Pacific. We'll have essentially 2 hours of training content and then break for lunch. We'll give you an hour break for lunch from 12 to 1 and resume at 1 p.m. Pacific time. That last block will again be 2 hours of training content. We're going to try to kind of break at the end of every hour and give you an opportunity to ask questions. We'll see how that goes, at the beginning of today, and we can adjust that as needed. Feel free to submit your questions in the Q&A box, and I think Marcos can also unmute you if you'd like to ask those questions verbally. As far as content goes for this training webinar, this is essentially a more granular overview of what we'll be covering. The first day here is going to focus more so on cryptography. We like to start at the lower level and build up. And then as we get into tomorrow, we'll be moving into some of the higher level SSL and TLS and protocols and some of the things around wolfSSL as a TLS library. So that kind of gives you an overview of our training webinar. We'll kind of dive into our content. Up next is our overview of wolfSSL. I am going to be switching between slides here, so hopefully that's not too interruptive. All right, so this is an introduction to wolfSSL as a company to provide you a foundation with who we are, where we are, what our products are, and some of the things we focus on. So we focus on securing data around the internet. As you can imagine, cryptography and SSL and TLS are very horizontal. So we end up going into a lot of different vertical markets. Some of those you can see here on this slide. So we have users of wolfSSL products in all these different markets and more. We secure data at rest with cryptography, data in transit using protocols like TLS, SSH. Typically, that's done over TCP/IP, but that can be really over any kind of transport medium that you have available. And then mixing some of those together with secure firmware updates. We have a wolfBoot product, which is a secure bootloader. And then, customers typically mix in a secure transport protocol to get the firmware image down to the device. So those are the three main areas we focus on. You'll see some of our products that fit into these categories here in a few slides. As a company, we were founded in 2004 in Bozeman, Montana. So that's right in the Rocky Mountains in the United States. We have over 2,000 commercial customers that use our products today, securing somewhere over 2 billion active connections at any one time on the internet. We were originally founded out of a need that the MySQL database had for an SSL library. They needed a clean room SSL library that they could safely ship with their commercial versions of MySQL. And so we wrote our first library, which is called YASL. That stood for yet another SSL. That was back in 2004. And in 2006, we rewrote that in C. YASL was originally written in C++. So we rewrote that in C. That was called CYASL, and then rebranded that in 2014 to wolfSSL, which is our current product today. We work with a lot of different technology partners, a lot of the silicon vendors, OS vendors, RTOS vendors, toolchain vendors. We like to make sure that wolfSSL works well out of the box on the platforms and operating systems that our customers are using. We also have a lot of open source partners. We like to make sure that wolfSSL builds well with open source products. Usually that's replacing the existing cryptography or TLS implementation there and providing a patch or upstreaming support for wolfSSL itself. This slide gives you an overview of our current products. So wolfSSL and wolfCrypt are kind of our primary and longest tenured products. All these products in the first row there are written in C. And so wolfCrypt kind of provides the foundation where we have all of our own cryptography implemented. We have some validations for FIPS 140-2. We're currently in the process of getting a 140-3 certificate. We have a DO-178C certification for avionics customers, and also an asynchronous crypto module to use on the server side with things like Intel Quick Assist and Cavium Nitrox. On top of wolfCrypt, it's wolfSSL. That's very portable, supports 30 to 40 operating systems now. That also includes an SSL sniffer tool, which allows you to inspect the traffic between a client and server. We have a Wolf MQTT, which is an MQTT client library, SSH server and client implementation called wolfSSH, a TPM 2.0 library called wolfTPM. wolfBoot is our secure bootloader. The newest product for us in the last year or so is wolfSentry. This is an embedded intrusion detection and prevention system. We wanted to bring the concepts, kind of a firewall and IP tables, fail to ban that Linux has down to the embedded level, giving you the ability to monitor a connection for malicious events, and when something happens, to take action on that, either based on a dynamic or static rule. And then we also have the author of curl on board. Daniel Stenberg is a wolfSSL engineer, so we offer commercial support and consulting for curl. We also have a version of curl meant for resource-constrained devices called tinycurl. And then in that second row, you see some language wrappers we have. These are wrappers around wolfSSL for Java, C#, Python, and JavaScript. All these products are dual licensed under commercial license and a GPL v2 or v3 open source license. This means you can easily download us from GitHub to prototype or even use us just under the open source license. And then it's essentially the same code base with a commercial license. The only thing that changes is the license headers. So you're getting essentially the same, functional code there. wolfSSL, this is our TLS library, supports up to the current standards of TLS 1.3 and DTLS 1.3. We try to make it as embedded friendly as we can. Footprint size typically ranges from 20 to 100 kilobytes, depending on what features you have enabled, what your compiler is, and what optimization level you're using. Runtime memory is typically 1 to 36 kilobytes per session. Footprint size, in comparison to OpenSSL can be up to 20 times smaller. So especially if you're trying to fit a TLS library down on an embedded resource constrained device, of course, that can be much easier. We support, like I said, 30 to 40 operating systems now. Most of definitely your standard Windows, Linux, Mac, most of your embedded RTOSs all the way down to a bare metal environment. Some benefits to wolfSSL customers are, time to market. Being more portable allows faster deployment times. We do have a Kickstart service that we can offer to help accelerate customer development. And that's something that we typically will take a customer hardware platform and software middleware internal and get wolfSSL up and running and send it back to the customer. We do offer commercial support with service level agreements and response times to quickly resolve issues. You can also, using wolfSSL provides you a good opportunity for cost reduction. Footprint sizes are smaller. And another thing, we like to highlight is our vulnerability fix time is very quick. Average time to fix is around 36 hours. And so that allows you to maintain a more secure product on your side. Some additional features of wolfSSL, we do offer validated and certified versions of wolfCrypt for FIPS 140-2 and 140-3, hopefully soon in the future. Like I mentioned, our DO-178C certificate, and we can also do just individual NIST CAVP algorithm validations using the ACVP protocol. Sometimes those are needed when you're going on to a further common criteria validation or something like that. We have what we call an OpenSSL compatibility layer. So this is essentially a subset of the OpenSSL APIs that we have the same prototype. And then we implement our own logic underneath that maps down to wolfSSL code internally. And so it allows an application to essentially call the same function names that you would expect from OpenSSL. And it can provide sometimes a pretty great path from migrating from OpenSSL over to wolfSSL easily. To help our server-side customers, we've integrated wolfSSL into most of the popular web servers today. And you can think Nginx, Apache, Lite, Mongoose are some examples there. We like to take advantage of hardware cryptography support when it's available on the platform. So this can provide performance improvements, anywhere from 5 to 10 times on embedded platforms. It can also provide footprint size reductions, since you can compile out the software code for that crypto algorithm. Also, in helping our customers migrate from OpenSSL to wolfSSL, we provide an OpenSSL engine we call Wolf Engine. And so this is an engine. OpenSSL has an engine framework where you can plug cryptography in underneath it. So this is wrapping wolfCrypt and wolfCrypt FIPS to kind of shim underneath OpenSSL. OpenSSL 3.x with their 3.0 and 3.1 have a provider architecture instead of an engine. And so we do offer a separate product for that called Wolf Provider, which does the same thing and wraps wolfCrypt, allowing it to plug underneath OpenSSL 3.x. One of the things that we were pretty excited about in the last few years is the advancement of TLS 1.3. It was awarded RFC 8446, and it gives some great advantages to users in the form of more security and better performance. We've got actually a kind of a slide deck that we'll dive into this in more detail. But if you want to learn more ahead of time, you can go to wolfSSL.com/TLS13, and that's a good starting point for learning more about wolfSSL's integration here. wolfCrypt sits underneath wolfSSL. This slide shows you the algorithms that we have implemented here. Pretty much all of your standard algorithms, as well as some more progressive ones like Cha-Cha 20, Poly 1305, and Curve Ed 25519. And these can be used in a modular manner where you can compile out pretty much all algorithms you don't need, leaving you with just the algorithms that you do need to help save footprint size. So I mentioned hardware cryptography can help you decrease your library footprint size and increase performance. We do support a number of different embedded targets here. We'll go into some more details in later slides as well, as far as how this integration happens and what we do have support for. This graph is just showing you kind of an example of performance comparison between software and hardware crypto. This is just on one of our platforms that we've worked with. It's an NXPK60 running at 100 megahertz. You can see this is throughput of each algorithm listed on the x-axis, and then the y-axis is throughput in megabytes per second. So software crypto is in blue and hardware crypto is in red. wolfMQTT is our MQTT client library. Here we have support for the 3.1.1 protocol as well as the 5.0 specification. We support quality of service levels 0 through 2. You can run either just over a insecure TCP connection or over TLS, which turns it into secure MQTT. And that TLS is, of course, wolfSSL when you're bundling together with wolfMQTT here. We've got some examples that we bundle with this to make it easier to get started. Client for blocking and non-blocking IO, a firmware example, some examples for Azure and AWS, IBM Watson, and also one using the sensor network specification, MQTT-SN. Total size here is pretty small, 3.6 kilobytes. And you can also shim wolfCrypt FIPS underneath this for those that need that there. wolfBoot is our secure bootloader. We've had this around for a few years now, and we continue to add more and more platform support to this. It's essentially a generic secure boot solution that uses kind of a dual bank or dual partition architecture, where you have your firmware, your main application firmware in one partition, and then an update partition where you would download the update image to. It uses safe coding practices with no heap use, so you can put it into safety critical applications more easily. It has an interruptible power fail-safe swap operation. So if your power fails or your device reboots during the update, you can say it'll safely roll back to your previous firmware image. It has some protection against downgrade attacks. And like I mentioned, also has the rollback mechanism, allowing you to return to a previous image state. It's very portable across OSs and RTOSs. Doesn't really have any requirements as far as additional hardware. It can update itself, so it has a self-update feature, and we include some tools that help you get started for key generation and signing your firmware image on the server side. You can chain load it if you have your own bootloaders in place that you need to, chain together and use wolfboot in a kind of in a more a larger system there. Some of our customers ask us how wolfboot compares to MCU boot. These are just a couple highlights here that we put together based on our research. So, you'll see more extensive algorithm support with wolfboot, and we can add more algorithms in if we don't support one that you need. More supported targets. So you can see we called in this slide, we just called out, some of our NXP targets specifically with Kinetis, LTC, and IMX, RT1060. OS agnostic down to the bare metal level. You can support secure elements underneath wolfboot. So if you want to store keys or use hardware crypto from those devices, whether that be a TPM 2.0 module or just a secure element like the LTC or the RT1060 has. There's a self-update feature, like I mentioned, for updating the bootloader itself. And you can plug in wolfCrypt's FIPS cryptography or DO178 underneath. wolfSSH, this is our SSH library. This used to be a library, only where we just provided examples for client and server integration. In the past year, we did produce a standalone server daemon we call wolfSSHD, which is kind of a production ready, out of the box server daemon that goes along and provides you wolfSSH support. In general, though, we've designed this to be very lightweight and embeddable, implementing the SSH v2 protocol. It supports both public key and password authentication, some common features that people like to see are, for file transfer, SFTP and SCP. We also support SSH agent and port forwarding support. Algorithms, we're going to be using wolfCrypt underneath. So you'll see a lot of the same algorithms in the list on the left that you saw back on our wolfCrypt slide. We do interop testing against other implementations we can find out there. Some of those include OpenSSH, PuTTY, FreeSSHD, and Bitvice. And of course, you can use wolfCrypt FIPS underneath wolfSSH as well. wolfSentry is our lightweight embedded IDPS solution. So like I mentioned, we essentially wanted to bring kind of the desktop server concepts down to embedded systems, providing you with a firewall type product that can be dynamic or static. You can define user-defined events. Those might be actions to take based on whatever condition you're meeting. One of those includes just shutting down the service completely. We've made it easier to use out of the box by integrating into wolfSSL, wolfMQTT, and wolfSSH, where in those products, you'll just have an enable wolfSentry build option, and that'll kind of pull in wolfSentry support internally to those products to make it easier to use. You can download this now from our product page. Just last year, we pushed out the first kind of stable release of this product. We like to do a lot of testing of wolfSSL. The more testing we can do, the fewer vulnerabilities and bugs make it out into our end releases and turn into fewer problems for you as our customers. So this is just we call the rainbow of testing. It has a bunch of different kinds of testing that we do, ranging from just simple API tests to peer review on our PRs, static analysis with things like scan build, memory leak checking with tools like Valgrind, doing interop testing against the other major implementations out there, testing all of our Cipher suites to make sure they're still working, as well as different types of certificates, doing regression testing to make sure we're not breaking things going forward. One interesting thing that we do is actually take our customer configurations internal to our testing system. And so we make sure those customer configurations that are actually being used aren't breaking from night to night, or even from PR to PR internally. The product testing is across other products on different OSs with different hardware acceleration, different compilers. We have 6 or 7 fuzzers now, at least internally, that we use to fuzz wolfCrypt and wolfSSL to try to find problems. We have a good network of third-party either organizations or individuals that help us test. So some of those are academics, some of those are test labs. And then we just have our open source community as well that can download our code and check it out and look at it. So I think we'll cover a few of these things as in the future content as well. But if you have any questions, feel free to let us know. This slide essentially calls out the same things, that we're doing a lot of testing. In the past year, one of our kind of big advancements was moving a lot of our testing into the Google Compute Engine, which allowed us to be more scalable and a little more efficient in testing, making our pull request tests and nightly tests finish quicker, so our development process is a little bit shorter internally. And you can download wolfSSL either from our website or from GitHub. We put our stable releases on our website. We also do tag those on GitHub. But if you're someone who likes to track our development progress, that's all available there on our GitHub repository. Okay, so I'm going to switch over now to our next slide deck. So one thing I like to do, at the beginning of our training courses is just kind of go over an overview of some of the acronyms that you'll see through the training course. And it can be a little test. When we do this in person, it's a little more interactive, but you can play along at home and see if you can guess the acronyms here as we go through them as well. So we've got, I don't know, I think 3 slides here, so it's not too long, and it's definitely not a comprehensive list of acronyms. So we'll start out with SSL. So this is the, one of the protocols that we implement. It stands for Secure Socket Layer. Its newer version is TLS. Stands for Transport Layer Security. DTLS is a version of TLS designed to run over unreliable protocols. That stands for Datagram TLS. PSK stands for Pre-Shared Keys that are pre-distributed to your endpoints. CRL stands for Certificate Revocation List, a way to check for certificates that have been revoked. And a newer and sometimes preferred method is OCSP, Online Certificate Status Protocol. That's a way of going out and dynamically at runtime checking the status of a certificate. DH, now we're getting into some crypto algorithms. Diffie-Hellman, RSA, a public key algorithm, Rivish, Shamir, and Edelman. ECC, also another public key algorithm. Elliptic curve cryptography. AES, now we're getting into a block cipher. Advanced encryption standard. DES, also a block cipher. Data encryption standard. SSH, now we're changing protocols here. Secure shell. The file transfer, that maybe gave part of that away, mechanism that SSH can use. SSH file transfer protocol. MQTT, another protocol. Message queuing telemetry transport. FIPS, which was mentioned a few times in our previous slide deck. Federal Information Processing Standard. Going along with FIPS is CAVP, Cryptographic Algorithm Validation Program. TPM, Trusted Platform Module. PKCS is a set of standards. Public key cryptography standards. All right, so those are some of the common ones that we see. You'll see those come up again, and hopefully by the end of the training course, you'll definitely have those, the understanding of those a little bit better if you haven't worked with them before. All right, so we're going to move on to our next category, which is an intro to cryptography. So we're going to go through various ciphers and algorithms, and what they are as far as categories, and then algorithms inside the categories, and then what those ciphers do. So as a larger category, you have cryptology. That's kind of broken down between cryptography and cryptanalysis. At wolfSSL, we're working predominantly in the cryptography side of this, implementing algorithms. So we have symmetric algorithms, asymmetric algorithms, hash functions, and then there's more functions and algorithm types as well that fit under cryptography. Some basic terminology: plain text. This is going to be the cipher, the text that's coming into your algorithm or cipher to be encrypted or encoded. Ciphertext is the encoded or encrypted output of those algorithms. A key is a unique, usually set of bytes or string that you use that is also an input to the algorithm. And then an IV is the initialization vector. Some of these algorithms require a little help in getting started. So if we go back to the very beginning of algorithms, which, the classic ciphers, as they're called, which are now insecure, kind of one of the more popular ones is the Caesar cipher, which is reportedly used by Julius Caesar. And it just encrypts messages by shifting each letter down 3 letters in the alphabet. So you can see it's very easy to break if you just shift the letters back up, the number of permutations that they went down. The Vignere cipher was created in the 16th century by Giovan Battista Bellasso. It was used in the Civil War as well as in World War I by the Swiss Army. And so this also shifts, using a shift to encrypt, but it's the shift increment is defined by a key. So here you can see ABC, ABC, that pattern repeats. It's a little bit more secure than just the Caesar cipher, but it has a lot of pattern repetition, so it really isn't very secure at all. And is there a perfect cipher? The closest thing you could get is a one-time pad, which would guarantee perfect secrecy, which essentially you're exclusive ORing a plain text with a random key, where the key is as long as the message, but that random key can only be used once, which doesn't really make it feasible for most use cases. And if we ask, well, what is a secure cipher? There's something called Kirchhoff's principle, which was stated by August Kirchhoff in the 19th century, which as a crypto system should be secure, even if everything about the system except the key is public knowledge. And so this is kind of what we operate on, being an open source company, that you can go and look at all of the algorithms that we've implemented. And as long as the keys that our customers are using are secret, the crypto system still maintains security. So we'll start out, the first larger category to look at here is symmetric algorithms. So a key is used for encryption, and then that same key is used for decryption, being the symmetric part of it. So you can see on the left side, we're encrypting data, it's our plain text coming in, the key as an input to the algorithm, putting out the ciphertext, and then the decryption operation just does the reverse. The second category is asymmetric algorithms. So here you have a key pair, which is a public and private key pair. One of those keys is used for encryption, and then the other one is used for decryption. So here you can see on the left, we're encrypting our plain text with a private key, where then on the right, we're decrypting that ciphertext using the public key. Next category is hash functions. So this is a one-way function which creates a unique digest. Sometimes you'll hear message digest in the context of these as a output. The digest is a fixed size depending on the algorithm that you're using, and you just have one input, the plain text, and then you get out the output out the other side. So now we'll dig into these in a little bit more depth. So starting with hash functions. So an ideal hash function creates a message digest that's easy to compute for your message, infeasible to generate a message that has a specific hash. It's infeasible to modify a message without changing the hash, and also infeasible to find two different messages with the same hash. So some common hash functions that you'll see are MD5 and all the SHAs. So SHA-1, SHA-256, 384, 512. Those are actually the SHA-256 to 512 are grouped under what's called SHA-2. And then there's also SHA-3 that came out. So you might see SHA-3-256 or SHA-3-384 as well. These are very versatile algorithms. They're used in a lot of different places. Some examples are digital signatures, public key encryption, integrity verification, message authentication, key agreement protocols, secure firmware updates, etc. The list goes on. If you've ever downloaded a file from a website, it's likely that you've seen a SHA sum accompany that, which is the SHA hash over that archive. So a good or an ideal hash function, even small differences in the input values will result in random looking output. So this is just an example of using the SHA-1 hash function, just to give you an idea of what that means. So here you can see the output digest for SHA of A, the SHA of the character B, and SHA of the character C. So you can see there, all those digests are very unique, even though A, B, and C are only changing by 1 bit in between them. So we have keyed hash functions, which is kind of the next step in security past hash functions. And so you can see that in the past category, anyone can use a hash function to compute a message digest. I could do it, and then I could have you do it, and we'd get the same message digest, which is exactly what it's designed to do. The keyed hash function is a hash function, but it also takes a key as an input. So it really limits the hash operation itself from being done by a specific party who has that key. This category of function provides the kind of the basis for MACs, message authentication codes, and also PRFs, which are pseudo-random functions. So into your MAC, you'll have the message as well as a key, and then output, you'll have the authentication tag, also known as the MAC. There's different ways to implement keyed hash functions. One is an HMAC, which stands for hash-based message authentication code. It uses a hash algorithm internally, for example, SHA-256. It's defined in the NIST FIPS 198-1 and RFC 2104 specifications. And the name of the algorithm is essentially what hash algorithm it's using. So HMAC SHA-256 is pretty obviously using SHA-256 internally. Another keyed hash function implementation is CMAC, which is a cipher-based message authentication code. This uses a block cipher internally and is defined in RFC 4493. An example of this, as you can see, is AES-CMAC. HMAC and CMAC mix together algorithms to make the outputting message authentication code. And there are some MACs or MAC algorithms that have dedicated designs that aren't mixing together sub-algorithms. So one of these is a fairly, somewhat newer in the scope of cryptography algorithm called Poly 1305, which was created by Daniel Bernstein in 2005. And this was optimized to be very fast on modern CPUs. Poly 1305 doesn't have a NIST standard yet. So that's one algorithm that people can't yet take through the FIPS process. But people who aren't locked down by validations and certifications can definitely use these types of algorithms. Symmetric algorithms, or what we'll look at next, specifically block ciphers. So these are algorithms that operate on a fixed length block of data. They use a symmetric key. They usually have several different operating modes to control how the blocks are chained together. So you've got examples of them are ECB, CBC, counter, and I think we'll go into some of those modes in here in a few slides. Commonly used block ciphers that you may see are AES, DES, triple DES, or GOST. Oh, here we go. Yep. So going through some of the modes of operation of these, ECB is kind of the most basic, which stands for electronic codebook mode. Sometimes this is known as direct as well. So you take the plain text and your key, you feed it through your algorithm, and you get your ciphertext. And so each block is encrypted separately from each other and not chained together in any way. The downside is, since there's no chaining between blocks, you can see a lot of patterns show up in the encrypted output. So these images here are from the Wikipedia article on block ciphers. And so I always like to use this because it makes it very obvious to see the original image on the left, the middle image encrypted using ECB mode. You can still see the patterns of Tux, the penguin, coming through. And then if you were to use a different mode besides ECB, you would see a much more random image or output, as you can see on the right. So to get a more random looking output and not have patterns show up, we start to chain together blocks. So the first chained block mode is CBC, which stands for cipher block chaining. And so you can see the output of the first block is fed in as an input to this encryption of the second block. And then since there's no block before the first block, we need to feed in an IV or initialization vector to kind of get the process started. The next mode of operation is called counter, or CTR. And so this uses a random key stream as an input, which you can see on the top of these diagrams, feeding in to the encryption algorithm, where the key comes in, and then it exclusive orders the plain text to get the ciphertext. And there's more types of block cipher modes. Those are just some of the more common ones that you might see. So next up is stream ciphers. And so this is a symmetric key cipher where plain text digits are exclusive ordered with a kind of a random key stream of bytes. An input to a stream cipher is a key and a nonce, where the key should be secret. It's usually 128 or 256 bits. But the nonce doesn't necessarily need to be secret, it just needs to be unique for each key. And a stream cipher will typically execute at a higher speed than a block cipher. So if you're looking for real-time performance, you don't have to worry about building up a block first before you encrypt. You can just be doing encryption byte by byte. Historically, these have had a lower complexity if you're going to implement an algorithm in hardware. And some examples here, you might see your RC4, ARC4, Rabbit, HC128, and SHA-20. Next category of symmetric algorithms is authenticated ciphers. And so an authenticated encryption it produces an authentication tag and also encrypts the message. See, we saw authentication tag show up earlier when we were talking about MACs. The authentication tag is a short string that should be impossible to guess without the key. It ensures the integrity of the message itself. When the key is only shared with one party, it can kind of have a side effect of authenticating the sender as well. And so you can see input to our algorithm is the key and the plain text, and the output is both a ciphertext and an authentication tag, where both of those are then fed into the decrypt operation. Depending on the cipher or the usage case, MACs and ciphers can be combined in 3 different ways. So you can encrypt and MAC, where you end up with a separate ciphertext and a tag. That's the diagram shown on the left. You can MAC then encrypt, where you MAC the plain text and feed that in as an input to the encryption operation. You just end up with a ciphertext then. Or on the right, you can encrypt then MAC, where you encrypt your plain text and then also do a MAC based on the encrypted value. So if we look at those in a little more detail, encrypt and MAC could potentially leak information about the plain text through the MAC itself, since the encrypted output hasn't been fed into the MAC operation. This is used by SSH. MAC then encrypt hides the plain text authentication tag, since you only ended up with a ciphertext as an output. This is used by TLS up to TLS 1.2. And then the last one, encrypt then MAC, the receiver only needs to compute the MAC to decrypt a corrupt message without decrypting the whole ciphertext. And this is available to TLS through an extension. Usually isn't on by default unless that implementation has it turned on. AEAD ciphers stands for Authenticated Encryption with Associated Data. This is an extension of authenticated encryption that takes both the plain text and unencrypted data used to generate the auth tag. So the unencrypted data is not encrypted as part of the operation. It's just some additional data you want to feed in to essentially be authenticated with the tag itself, but not encrypted. Associated data is this extra data. It's defined as any data processed by an authentication cipher, which is authenticated but not encrypted. A typical use case of an AEAD cipher is to protect protocols datagrams clear text headers, where you might not really be concerned about the header itself being encrypted, but you still want to verify the integrity of that header. For example, the subpoint there is that destination addresses need to remain unencrypted for routing to work correctly. So if we encrypted the header itself with the address, it wouldn't be able to be routed anymore unless you decrypted it. When using AEAD algorithms, you can choose to leave either the plain text or the authenticated data empty, and the algorithm will still work correctly. Some examples of these are AES GCM, CCM, and Poly 1305. So now we'll move to asymmetric algorithms. These are public key algorithms. They use 2 keys for encryption and decryption, a public and private key pair. Examples of these are things like RSA, ECC, or DSA. RSA, standing for Ribisch-Shmir-Edelman, was the first public key encryption scheme, which came out in 1977. It's still widely used around the internet, even though it's 40 years past when it came out, which is pretty amazing. It's used for both encryption and digital signatures. ECC is elliptic curve cryptography. This was introduced in 1985. It uses points on a mathematical curve, which is called an elliptic curve. There's many different types of elliptic curve definitions, and we'll see that later in our slides and training content here today and tomorrow. It provides encryption, signature generation, and key agreement. It's faster than historical algorithms typically, as compared to RSA or DSA, and uses less memory since the keys are smaller. The signature generation algorithm for ECC is called ECDSA. ECDH is key agreement, and ECIES is encryption. So just doing a quick comparison, RSA has the advantage of being well established and being around for so long. Most systems probably have support for RSA. ECC has been out for a while now too, but not as long as RSA. It has shorter keys with the same security level, can have lower CPU usage and lower memory usage as well, because the keys are smaller, specifically for memory use. And then, although not a public key algorithm, but sometimes used as an alternative, PSK or pre-shared keys avoids the public key operation completely, with either a benefit or a con of having extra key management. So the next asymmetric algorithm type is key agreement algorithms. So here you may have heard Diffie-Hellman, acronymed as DH. This was the first key agreement algorithm in 1976. This is used to establish a shared secret value between two parties. The secret can then be turned into one or more symmetric keys to be used in a later encryption operation. It must be used with a safe prime, which does take a while to generate. So typically, these would be generated up front and then stored in a file or something like that. The safe prime can take as much as 1,000 times longer to generate than RSA parameters of the same security. Algorithms under key agreement are DH Diffie-Hellman, and then there's the elliptic curve variant called ECDH. This is another diagram from Wikipedia, which I like to show just because its visual aspect. Kind of the security of a key agreement algorithm is based on the fact that you can't go backwards, even if you know one of the shared secrets. And so here you have Alice and Bob that have a common paint color, but they each have their own secret color. Those are mixed together to form the orange and the blue. That's transferred to the other party. And then when they mix that kind of shared color together with their own secret key or secret color again, they end up with a common secret, which is down at the bottom at the brown. Okay, so random number generation, this sits underneath a lot of other algorithms. And so there's some different terminology here that's good to know. First of all, entropy itself is a measure of uncertainty or disorder in a system. Having true entropy is very important, especially to the security of the upper level crypto system that lives on top of it. If you don't have true randomness, then a lot of the cryptography becomes predictable. And it turns out generating true entropy or true randomness is very hard. And there's a lot of bad ways to do it that we do see people tending to do from time to time, and hopefully try to correct them on that as well. Some people try to use constant numbers. Maybe they're doing that for testing, use a clock source, but likely, your boot time from when you boot your device to when you get to the operation is probably not that random. Some people try to use hardware serial and MAC numbers, but that can be very predictable. There's lots of examples, out there of people using RNGs or seeding them incorrectly. Just one that we noted here was in 2013. There was an issue on Android where applications were, if they didn't explicitly initialize the PRNG and seed it, it was using bad entropy. And so as a result of that, an application, essentially all the applications that were in that category, including things for key generation, signing, etc., weren't receiving strong random entropy values, and as such, the higher level algorithms were vulnerable. And so Google's fix was to recommend seeding your PRNG with dev-random or dev-urandom on Android devices. And I believe they fixed that as a default later on. So the takeaway there is to verify your RNG is seeded with a good entropy source. And the nice thing is it's becoming increasingly more common for a TRNG to be available in hardware. So if you're running on any of these platforms here plus more, you probably have a hardware RNG that you could use to seed a higher level PRNG. We've mentioned a couple of terms here. They're good to know. So as you see them, you can compare them and know where they fit. TRNG is a true random number generator. PRNG is a pseudo random number generator. And then DRBG is a deterministic random bit generator. So starting with a TRNG, this is usually derived from a natural source of entropy in hardware. It uses some kind of unpredictable process to produce output. That might be ring oscillators or noise diodes or radioactive decay. There's a lot of things that people use there. Like we mentioned, it's critically important for the higher level PRNG or DRBG to be seeded by a TRNG that has random entropy. Where it's possible, we recommend you use the one that's integrated into your processor. PRNG stands for pseudo random number generator. Output is based on a specific algorithm. It receives random bits or entropy as an input from some kind of entropy pool, and then expands those bits out into a longer sequence. So the benefit here is that the output is predictable given an initial state. And it must be seeded by a true random input. Otherwise, like that previous bullet point said, your output is always going to be the same. DRBG, this is essentially FIPS or NIST term for PRNG. Their special publication 800-90 defined 4 different DRBG implementations, one based on a hash, one based on an HMAC, one based on a counter, AES counter, and then dual EC-DRBG. A few years back, the dual EC-DRBG was unveiled to be backdoored as part of the NSA Bull Run project. And so that one's kind of dropped off the list and hopefully gone away. wolfCrypt itself implements the hash DRBG from this specification. Now, when you're working with algorithms, you do have a choice in key sizes. That can be either matched up to your requirements, or maybe you're just trying to meet, a certain level of security. NIST does have a recommended key size diagram. I pulled this table out of one of their documents. So for a certain level of a bit level of security, so for example, you were targeting a 256 bits of security, these would be the key sizes you would need for all these different algorithms. So for example, AES 256, SHA-512, RSA 15360, and ECC 521. Obviously, you can see some of those larger RSA key sizes probably aren't feasible on a lot of platforms, or not really used. So in that case, people would probably choose to use ECC 521 there instead. But a good thing to note here is that your bit level of security is really only as good as your lowest level. So if you were using AES 128, you really only had 128 bits of security. There's this website that I found a while back, keylength.com. Not really recommending it, but it could be a good reference to look at. It just kind of calls out some of the different key length recommendations from different bodies or standards bodies around the world. And then along with algorithms, secure storage. So how do you store your data at rest? You should definitely take precaution when storing sensitive data, which might be things like user data, passwords, or certificates and keys. And it's a good practice to encrypt that, of course, when it's at rest. The security of the whole system depends on the private key being private. There's some different ways to handle that users and customers do. Some people embed it in the firmware from the factory. Some people transfer it to the embedded device from a secure key server. And sometimes it's just generated on the device as part of provisioning, and then it always stays on the device. Sometimes that last one, may be the best, especially if you can generate it inside of like a TPM module or some kind of secure enclave. Good practices, you should use different keys for different purposes. So if you might not want to use the same key for signing something as you do for using in your TLS session. And then keys should change often to help minimize your vulnerability exposure. Often here is really relative to what makes sense for your application and use case. How to store keys securely. The ideal scenario is you have a secure element like a TPM or an HSM or something else that you can store the key into. Otherwise, there's some different approaches you could take. If your system's attended, you could require user input to decrypt the keys. If your system's unattended, there might be some other countermeasures you could take. Maybe you could automatically zero out keys if you detect tampering, or use some kind of crypto system that automatically zeroes out the keys for you. Now, also in relation to algorithms, different algorithms perform differently. So you have some choices here as far as performance goes when you're choosing an algorithm. And I just wanted to put this in here more so that you keep this in mind and don't just think all algorithms perform the same. As you can see here, this is just a kind of a quick snapshot we took of some of our algorithms in wolfCrypt. They're on the x-axis there, the algorithm name, and the y-axis is throughput in megabytes per second. So you can see, as you compare some of those algorithms, for example, AES GCM is a lot slower than AES Direct. Or, of course, these are different categories of algorithms too. So you're probably not going to, use them all in the same place. And then keep in mind, hardware crypto can also help speed these up if you've got that available on your target. All right, so that brings us to the end of this slide deck. I think we'd like to open it up for a quick question set. Look at some of the features, look at the structure that you'll see when you download the product, and a few other things. There's a few of these slides that are duplicated here, so I won't read them to you again. Just an overview of wolfSSL, some of the features we went through earlier. We have ported wolfSSL into a lot of open source projects. We didn't have the slide on the previous one. This gives you some idea of a few of the ones we've done. So we have patches available, or we've upstreamed that support depending on the project for all these plus more, which is kind of nice, especially if you want to put FIPS cryptography underneath any of these things. If you want to see our patches we have for open source projects, we have a separate repository. I linked it here at the bottom of this slide. It's called OSP. If you go to our wolfSSL GitHub organization and then OSP underneath that. Again, telling you the algorithms supported by wolfCrypt, where to get them from our website or from GitHub. So here's our package structure. So when you download wolfSSL, you'll see something like this. It used to be smaller, but it's grown to the point where I think it's helpful to walk through some of the main areas of it. So we'll go through these slides, and then I might open up a terminal and walk through it again just to solidify it in your mind. So the first one kind of at the top is the IDE directory. This is where all of our compiler project files live. If you want to open up wolfCrypt as a project in your favorite IDE or compiler studio, this is probably where you want to go. If you want to open up a project for Eclipse or IREWarm or Raleigh Crossworks or Kyle's MDK tools, you can just open it up, hit build, and you'll end up with a library artifact. If we go down, you'll see a certs directory. This has example certificates and keys that we bundle with wolfSSL. We, of course, don't intend or recommend at all that you use these in production environments, but can be helpful when you're getting up and running and testing and prototyping. We use them internally for testing. So it'll include certificates and keys for both the server and the client side. for both RSA and ECC, and probably some others algorithms in there as well. Certificates and keys for CAs, different bit levels. So RSA 1024, 2048. It has some example certificate revocation lists, CRLs in there, some example Diffie-Hellman parameter files. So just some generally useful stuff to help you get up and running more quickly with tests. wolfSSL uses AutoComp for configuration. So there's a configure script there, which will be used on Linux, Unix type systems. You'll notice we have a CTOCrypt and a CASL directory. So as I mentioned earlier, wolfSSL used to be called CASL and wolfCrypt used to be called CTOCrypt around pre-2014. And so we essentially have a small compatibility layer here for if there are older users still using the old CASL API. It maps those essentially down to the newer wolfSSL API. We don't recommend using those for new projects. There's an examples directory. This is a good place to start for both seeing how wolfSSL applications can be written, also can provide one source of reference for API usage. We have an example client, server, echo client, and echo server in this directory. And we also have some additional examples that are they're smaller, kind of per feature or function in our wolfSSL-examples repository. So I've linked that here for you under our wolfSSL GitHub account. gencertbuff is .pl. This is a Perl script. Oftentimes, a good amount of embedded devices won't have a file system. And so you need a way to get your files converted into a C array. So this is one route to do that. You can modify this. It'll generate a header file called wolfSSL/certs_test.h and essentially convert your files for keys and certs into C arrays or buffers. So we'll skip down now to the wolfCrypt directory. That's our source file directory for cryptography sources of wolfCrypt. The wolfSSL subdirectory is our header or include directory. Our SSL TLS headers are just right under wolfSSL. Crypto headers are under wolfSSL/wolfCrypt. And OpenSSL compatibility layer is under wolfSSL/OpenSSL. At the bottom, you can see some Visual Studio solution files. If you're on Windows, you can open one of those guys up and you'll be able to build either the wolfSSL library project or also some of our examples. And then down at the very bottom, there's a directory called wrapper. This contains our C# wrapper for wolfSSL. We do have wrappers for Java, Python, JavaScript, Go, but just because those are bigger in size, we don't bundle those inside of wolfSSL. Those are distributed as a separate download package. So a couple notes on thread safety. If you're using wolfSSL in a multi-threaded environment, that's safe to do. You just have to keep a couple things in mind. So in general, multiple threads can enter the library simultaneously without causing conflicts. We try to avoid using global data or static data or things that would make that not work. There's two exceptions to this that you do need to keep in mind when using wolfSSL in a multi-threaded environment. The first one of these is that you do need to synchronize access to the wolfSSL session structure. So we're trying to, for example, read and write to one wolfSSL structure from two different threads at the same time isn't supported and is going to cause you problems. So anytime you're accessing that session between threads, you should synchronize that with a lock. The second exception case is in relation to what we have as a wolfSSL context. So a wolfSSL context is kind of a factory for sessions. You'll set a lot of your settings and certs and keys up in the context first. And so you do need to completely initialize that before you start making individual sessions from it with wolfSSL new. If you don't, then when wolfSSL new is called, it copies essentially some of the settings from the context, and you might end up with an impartial session structure. And so what we recommend doing is just having a single thread initialize the context, or have some kind of locking around that, and then go off and do your multi-threaded operations and creating sessions from that in subsequent areas of your code. The wolfSSL package does include a number of automated tests. So you can run make check, and these will run for you. We run this all the time. Our engineers do internally when we're working on the code. And they're kind of built in for us as part of our commit tests. So every time we do a commit, we get all these tests to run, plus a few more. There's an OpenSSL interop test, which does some interop between our examples and OpenSSL's applications. There's a session resumption test that tries resuming sessions at the TLS layer. We have a test suite, which runs our wolfCrypt test application, and then a simple client and server test. We've got an external test, which goes and uses our example client and connects out to an external web server. We do a Google interop test to make sure our wolfSSLs can connect to Google servers okay, just since those are very commonly used and usually readily available. And then unit tests also for most of our APIs. If you're curious in what specific RFCs we're implementing code off of, we do have that documented inside of our manual. I believe it's Appendix B, but we just redid our manual in the last year, so there's a chance this could have moved, but I think it's in the same spot. It'll be obvious when you look at the table of contents in the wolfSSL manual. Okay, so I was just gonna step out of my slides and just show you a interactive view of the wolfSSL package. So I just cloned wolfSSL from GitHub here. You can see we've got pretty much the same structure that I described to you before. We may have a couple newer things in here that we haven't added to that previous slide yet. But kind of our configure script, which we'll be looking at later, is generated off configure.ac. So if you're curious what any options do internally, you can search in here for, for example, GCM, enable ESGCM. You can see we've got some new things. We've got a Zephyr directory for users on Zephyr. Some of the things we put in have been put in the root directory, just at a historical location, and we might migrate those at some point. Like for example, TI-RTOS is specific to TI-RTOS users. We have also some MP-LabX for microchip customers, MQX, which was Freescaler originally, now in NXP. There's our examples directory, our old CYASL and CTAU crypt compatibility layer. Our doc directory has also includes Doxygen comments. We split out our header files, so we actually have a different copy of our header files under docs comments header files, just so we don't kind of blow up the size of our normal header files, but we still give our users the Doxygen API docs for each of these algorithms. What else is interesting? SSL Sniffer has our SSL Sniffer product. That's just kind of a passive sniffer that you can load in the private key from the server to decrypt traffic from. Some helpful files if you're looking to run wolfSSL and wolfCrypt inside of the Linux kernel as a kernel module. Some support for CMAC users. One thing you need to do if you do clone wolfSSL from GitHub, you need to run autogen.sh as a first step. I think we do cover that as well. And we have a building wolfSSL slide deck here coming out. IPP is specific to Intel's IPP compiler. I mentioned IDE directory has a lot of our IDE projects. Docker is a newer directory for us. We've started to add some Docker support, especially around testing more recently inside of wolfSSL. Okay, so we'll come back and look at the wolfSSL directory and do some more stuff there as we progress through our slides here. But we're going to move on to building wolfSSL first, and then we'll come back and build the library. Well, there's a lot of different compilers and suites out there that people are using to build wolfSSL. The kind of the default or most commonly used way that we do internally and most of our customers use is using the AutoConf system. So you probably can encounter this somewhere. There's a lot of open source packages that use AutoConf for configuration. So essentially you run /configure with any number of options, which are usually in the form of a -- enable or a -- disable. And that goes out and checks a bunch of stuff about your system that we can then use during compilation. You run make to compile the library, and then either make install or sudo make install to install the library artifacts, header files, and a few other things. You can use a -- help argument to configure, which will list out all of our currently supported enable options. We have a lot of these now. We probably have a couple hundred. You can imagine, every algorithm mode, hardware crypto, all kinds of stuff. We allow you pretty fine-grained, customizability to enable or disable or change how it works. Once you've selected your enable options, you just append them to the configure line using -- enable. So here we're enabling ECC and enabling DTLS support. If you do need to pass preprocessor defines through configure, you can do that using the cflags variable. So here we're defining a define called example_define. There's some cases where we have defines in the code, but we don't have enable options for them, and you'll need to pass them through the cflags. Usually that's more on the edge case side of things as far as functionality goes. You can run make check. That runs the test that I covered earlier with our automated tests. It'll tell you, how many passed, how many failed. And some of them will be skipped by default. For example, the OpenSSL test, I think we have disabled by default just because everyone doesn't have OpenSSL on the system, or there's some behavior differences even between OpenSSL versions. And then you'd install the library using make install or sudo make install. By default, we're going to install our artifacts into user local include wolfSSL. That's where the headers will go. And user local lib is where the library artifacts will go. The library is called libwolfSSL.so or .dylib is the shared library if you're on Linux, Unix, or Mac. And then the static library is libwolfSSL.a. I mentioned we have some Visual Studio solution files if you're on Windows. The first one there is a little bit older. It's wolfSSL-ntrue, which originally was using the ntrue post-quantum algorithm, which we've had support for a number of years, really before kind of the big migration to post-quantum and the activity around that started. We've got a wolfSSL.solution for a 32-bit library and project, and a 64-bit library and project solution as well. Those solutions include a number of projects for our examples: client server, client echo server, sniffer, test suite, and the library proper. If you want some more details on Visual Studio, we've got kind of a walkthrough available on our website, which has some screenshots and some more details there. Users on Windows who use Cygwin can also build wolfSSL. That you're going to follow the AutoConf instructions using configure, make install. The required Cygwin packages you'll need are GCC, automake, AutoConf, libtool, make, and unzip. I guess we do have a couple slides here on Visual Studio. So here's what it would look like if you open up the project file. You might need to upgrade those projects depending on your Visual Studio version. Then you could debug and run an example by right-clicking on the example, going to debug and start new instance. You could run our example client against our example server by opening up two instances of Visual Studio or two command prompt windows, and then running one against the other. You can generate DLLs, and you can There we have configuration options between switching between DLL debug and DLL release in the build configurations, as you can see here on the right side. The DLLs generated will be inside of the wolfSSL package under the DLL debug or DLL release directory. Then if you drop into there, that's where you'll see the wolfSSL.dll. There's also a lot of different compilers and suites that people like to use. We do have an install file in the root directory that points you kind of in the right direction for a lot of those. For example, if you want to use CMAC, that would be a good first place to look. Or if you want to use, build for Arduino, there's some notes in there about how you would go about starting that. The other type of use case that people like to use us in is actually pull our files directly into their own IDE project. And so that's perfectly fine to do instead of building a library artifact. The only thing you'll just need to make sure is that you pull in the right files. So you'll find our SSL and TLS source files under the ./source directory, the SSL and TLS header files under the ./wolfSSL subdirectory, the crypto source files under wolfCrypt/source, and the crypto header files under wolfSSL/wolfCrypt. And there are some files that you can conditionally compile in depending on feature set. Most of the time that comes into play when there's assembly optimizations being used, and only certain files apply to certain architectures. As we've been developing and advancing wolfSSL, we've tried to keep portability in mind as a primary design goal. So we've tried to abstract out pretty much all of the dependencies that you would have on the platform or the system, as far as OS, transport layer, etc. Some of those are listed in green here, as far as things like I/O, logging, memory, data types, NENS, etc. And we'll see how you can override some of those and use those abstraction layers later on in our training course. If you want to see our existing port layers that we have most of those listed in our wolfSSL/wolfCrypt/settings.h header, and you'll see usually one defined kind of per platform. So if you're building for FreeRTOS, there's a define called FreeRTOS. If you're on LWIP, there's a wolfSSL_LWIP. And so you could either uncomment those there, or what we would recommend typically more so in an embedded case is using a custom user settings file, which we'll also talk about in a little bit. Which I guess a little bit is right here. So there's a way for wolfSSL to include a custom header file called user_settings.h. And that way is just to build wolfSSL with wolfSSL_user_settings defined. And then what this enables you to do is put all of your customizations for wolfSSL into that header file. And it allows you just to maintain that one single header file as you update from release to release of wolfSSL. And it also can make it a little bit easier where you don't have to put all those defines on if you're using autoconf like on the C flags line. We have some example user settings that you can look at as a reference. There's kind of a good comprehensive one under the IDE Raleigh Crossworks ARM directory. And then we also have some pre-made examples under examples/configs. We have a user settings that kind of enables all features. There's one that is a minimum build using ECC. And then there's one that we use for our wolfboot product and building for key tools that are distributed with wolfboot. Okay, so let's drop into my shell again here. Okay, so I mentioned the first thing you're going to want to do when you download from Git or GitHub is run autogen.sh. So this will generate the configure script for you. It runs auto recomp internally and sets up a couple things. And if you're using one of our stable releases from our website, you won't have autogen.sh and you won't need to run it since configure is already there. We can run configure. I mentioned we can run --help, and that'll list out all of our options that we have available to you. It's a pretty big list now, as I mentioned. Algorithms, math libraries, algorithm modes, features. Let's just do a basic build with configure. No options. That runs the build that we kind of have as our recommended build out of the box for Linux, Unix type systems. So it's going out and detecting a bunch of stuff about the system. Here I'm building on a Mac, but process would be pretty much identical if you were on Linux or Unix. It gives you a nice summary at the end of your build. As far as at the top of this list, it shows you information about your compiler and your CPU and the C flags that were used. Then it has a big list of features. So it tells you what's enabled and what's disabled. So just looking at the top couple here, you can see, we have file system enabled. We have side channel hardening enabled. We're using our SP math library, which is our underlying math implementation. We're allowing assembly, and AES is enabled. The list goes on and on. So we can build the library running make. This builds the library as well as the examples, the test suite, the wolfCrypt test, and the wolfCrypt benchmark. And then if we wanted to install it, we would run a sudo make install or a make install. If you want to redirect it to in different installation path, you can use prefix equals and give it a path to your install directory. That can be helpful if you've got multiple versions of wolfSSL on a system, or you're trying to package it in a specific manner. If we want to compile just the library, we can do that by running make source/libwolfSSL.la. Sometimes that's helpful if you're cross-compiling and you don't want to compile the examples or the tests or some of the things that are a little less portable to different platforms. But yeah, that should just stop for us right after the library here. Library artifacts, when they're not installed yet, are located in source.libs. Here you can see, since I'm on a Mac, I've got a .dylib for the shared library. I mentioned some files are kind of conditional per architecture. If we look under wolfCrypt source, you can see, let me do a make clean here, so we don't see the object files. We have some assembly files up here. Oh, here they are. They're obviously kind of architecture specific as far as ARM32 or 64 or x86 64, etc. You should be able, if you're pulling those into your IDE project, you can include those, and they'll only be compiled if the right defines are set. The only ones I think that you'll need to exclude if you're explicitly pulling them in are, we have some files that are specific to Intel AES-NI. Some of these top ones, these AES, ASM, ones that end in .s, you might need to exclude unless you're running on an Intel system. Okay, so back to our slide decks. Next, we're on to our wolfCrypt test and benchmark applications. So these are two applications that we ship with wolfSSL out of the box. They're both very helpful for different reasons. The test application essentially runs, wolfCrypt test, I should say cryptography test vectors through all of the wolfCrypt algorithms that are enabled by default. And so it makes sure the crypto is working correctly on your platform. This is really, we recommend doing this as a first thing when you're trying to get wolfSSL and wolfCrypt running on your device or platform, I should say. If the crypto doesn't work correctly, then you're going to definitely run into higher level problems at the TLS level or other protocol level, which are not going to be extremely obvious until you drop back down to the crypto level and make sure that's working. The wolfCrypt test is compiled when you run make. The executable is called test wolfCrypt and located under the wolfCrypt/test directory. When you run it, you're going to see some output that just essentially says each test passed, or if a test failed, that would also be called out there. The second application that we distribute is the benchmark application. And so this allows you to essentially benchmark algorithms on your target. So all the enabled algorithms will be benchmarked by default. We run this on a lot of targets that we port to, and we post some reference benchmarks on a web page on our website. I've linked that here on the bottom as kind of a reference for you if you'd like. This is compiled just when running a normal make as well. The executable is called benchmark and located under wolfCrypt/benchmark. When you run it, you're going to see throughput of each algorithm, typically in megabytes per second, or it switches to operations per second when you get down to public key algorithms. If you're on a supported processor, you'll see cycles per byte for each algorithm, which is kind of neat to see. And it just benchmarks each algorithm for 1 second. So both of those are portable to embedded devices, but out of the box, they kind of are set up to assume they're running on a desktop-like system. So they do include a main function in each of those files. They use certificate and key files. If your embedded device doesn't have a file system, that could be a concern. But we have a way to switch that, you'll see. And then it does run all algorithms tests or all algorithm benchmarks by default. So if you're on an embedded target, you can customize this. You can define bench embedded when you're compiling wolfSSL or the application. And what this does is reduce memory usage of each of those applications, essentially uses smaller buffer sizes to be more resource friendly. And then if you don't have a file system available, or maybe you just don't want to worry about copying certificate and key files over to your device, you can define one of the defines here, either use cert buffers 1024, 2048, or 256. And that'll cause the test and the benchmark to use certificate buffers instead of files. The 1024 one is using RSA 1024, 2048 is using RSA 2048, and the 256 one is using ECC P256. So if you have your own embedded target, you probably have your own driver or entry point already. In that case, you want to compile out the main function in test.c or benchmark.c, and you can do that by defining known main driver. When you do that, it'll expose an entry point for you to call from your driver code. That's either going to be called wolfCrypt_test or benchmark_test. And then you can either call those entry point functions, or you can run individual algorithm tests or benchmarks using a respective, more specific function, like you can see on the bottom here per algorithm. One thing to note, when you're building through AutoConf with configure and make, the executables that you're running, so say the test wolfCrypt executable is actually a wrapper script that AutoConf sets up to help it find and set the right paths. The actual executable is at wolfCrypt/test/.libs/test_wolfCrypt. If you're building a static library instead of a shared library, this won't be the case, and test wolfCrypt will actually be an executable. That's good to keep in mind, especially if you're trying to use external tools with those applications like Valgrind, or run it through GDB or LLDB. Okay, so let's drop into the shell and give that a quick run here. So I think we made our, we have to make clean, since we only built the library last time, we have to redo. Actually, we can use the same configuration and just run a make, because we want to build the wolfCrypt test and the wolfCrypt benchmark, since we're going to be running those. We can run wolfCrypt test wolfCrypt. Looks like all of our tests passed, and it gives you the version number that you're on. This is wolfSSL version 554. wolfCrypt benchmark, we run in the same way, wolfCrypt/benchmark/benchmark. And this goes out and benchmarks each algorithm for 1 second. It shows you throughput, megabytes per second, cycles per byte. Pretty granular as far as modes of algorithms go. And this can be helpful if you're comparing hardware cryptography. We use this a lot when we'll run it with software crypto, enable the hardware crypto on a certain device, run it again, and then you can see the delta in performance there. It's also helpful when you're configuring the underlying math library differently. So we have 3 different math libraries now: big integer, fast math, and SB math. And And each of those can be configured slightly differently, and they'll change the performance of the public key operations. So there you can see it when we get to the bottom, the metric changed to operations per second instead of megabytes per second for public keys. If we take a quick look at the wolfCrypt test, I mentioned there's a no main driver defined in here, which essentially compiles out the main function. There's a function called wolfCrypt test that your application can call as an entry point into the wolfCrypt test. And then you can also see there's functions per algorithm for running just AES test, or if you only want to run like a CMAC test or an AES GCM test. The wolfCrypt benchmark does have some options you can use to it. So I won't go through all these options, but if you want to print out this output in Japanese, or if you want to output in a CSV friendly format, or then you can just dump it into a more easily exportable if you want to put it into a table for distribution. You can benchmark individual algorithms. So if we only want to benchmark AES CBC, we can do AES-CBC, and we're just going to benchmark that. So that can speed up your runtime a little bit of the benchmark if you're only concerned with certain things. And you've got some more configure options there, but just to note, they're available there for you. I don't believe the wolfCrypt test has any options available. No, it just runs. All right, so let's see. Our next topic here was going to be, we've got about 9 minutes till our lunch break. I guess we'll get through random number generation here, and then we'll take a break after this. So from here, we're going to go down into talking about the wolfCrypt APIs for different crypto layer operations. Starting at the very bottom, in my mind, is the RNG, since that sits underneath some of the other operations would. So we covered, how random numbers are important, and you're the one on RNG to be seeded with random entropy. wolfCrypt has a PRNG implementation that we've implemented based on the SB 800-90A's hash DRBG specification. It's enabled by default in wolfCrypt, and you can disable it by defining no RNG, but that's a pretty unlikely case that someone would do that. The main header file for our RNG is in wolfSSL/wolfCrypt/random.h. And there's one main structure called WC_RNG. When you're looking to use the RNG, you want to initialize the WC_RNG structure using one of these init RNG functions. Either the first one is a normal one, or you'll notice we have a lot of extended functions which are denoted by the _EX. And so these typically take extra arguments. In this case, this is taking a heap pointer and a dev ID, as we call it. The heap pointer is if you're going to be using your own heap and you don't want to use just the normal heap on the system. Dev ID, you'll see I guess in a little bit later session, is specific to something we have called crypto callbacks. So it's a way to use an ID for calling down into an underlying crypto provider. You can initialize the RNG with a nonce if you want to add in extra entropy using the init RNG nonce function in place of that initial init RNG. And then when you're all done with the WC RNG structure, you would free it up with WC_free RNG. When you're ready to generate some random data, you can call WC RNG generate byte, which generates a single byte of entropy. Or you can generate a block of entropy, which is likely a more common scenario, where you can tell it a certain size of bytes to generate, and it'll generate randomness and put it into your output buffer. wolfCrypt test does have a random test function you can use as a reference of API usage. And we also have our Doxygen API documentation around our RNG. So if you're interested in how our PRNG is seeded, internally we call a function called WC generate seed, which is responsible for going to the system and getting entropy. And how it does that is variable between what system you're running on. You can also override this process. There's a couple defines. We have custom ran generate seed, custom ran generate seed OS, and custom ran generate. So the first of these, custom ran generate seed, you can define this to your own function. For example, in the comment here, you're seeing that we're defining it to a function called ran gen seed. And what we'll do then is our code will essentially just call that whatever that's defined to. As you can see in the bottom snippet there, we're returning the call to your custom ran generate seed with an output buffer and a size. So we expect that function to return size bytes into output. Second function here is custom ran generate seed OS. And so what this does is it's the same as the last one, except you also are getting a third argument called OS seed, which is a pointer to an OS seed structure. That's one of our structures that in case you need some extra information inside of your function that you need to grab from your platform to get entropy. Again, then generate your entropy of size bytes and place it into output. The third option here is to define custom ran generate. So you can see the comment, we're defining it to a function called rand_gen. And what this does is just generate one single byte at a time. And so this snippet of code on the bottom is in what we're doing internal to wolfCrypt. And you can see I've bolded the call to custom ran generate, where we're actually just going to loop around and keep calling custom ran generate until we get as many bytes as we're looking for. Half of our day here, we're going to continue into more crypto level overviews of wolfCrypt APIs for different operations. So we'll go through some of those for message digest, block ciphers, digital signatures, key agreement algorithms, password-based key derivation functions or PBKDF. Then we might look at some PKCS and CMS, as well as our more into FIPS 140-2 and -3. We'll see how the time goes though, and where we get. So our next category is message digest and HMACs. If you remember, we're just coming off random numbers here in our previous half. And so wolfCrypt provides, most of the message digest algorithms you'd be looking to use today. We have an enable option per algorithm. So, -- enable SHA, for example. Underneath, there is an associated define if you're not using configure. I've tried to document those here in the second column. And some of these are negative defines. So, for example, SHA is enabled by default unless you disable it. And so there's actually, the define is actually no SHA, which you would only use if you wanted to disable SHA from the library. Whereas, conversely, some of the other ones like SHA-512 is disabled by default until you enable it with wolfSSL _ SHA-512 or enable SHA-512. We have SHA-224 and SHA-3 enabled on x86 and AR64 by default. They'll be disabled on other platforms unless you switch them on manually. Now, if we look at the API usage, it's going to be similar to the RNG in that there's kind of one header file per each algorithm. So for SHA, there's wolfSSL wolfCrypt SHA.h, and there's one structure called WC _SHA. When using SHA, you'll want to initialize the structure with one of our init SHA functions, either the default, the extended with a heap pointer and dev ID. After you're done, you can free the SHA structure with SHA free. In the middle, as you're using it, you can update as many times as you need to by passing in more data consecutively. You can do that using the WC SHA update function. So that allows you to not have to read in your entire, image or buffer, or whatever you're doing an update over, and just to kind of chunk it up and save memory. When you're all done and ready to compute the final digest, call it WC SHA final, and wolfCrypt will place that final digest into the output buffer for you. There's no size argument here, since each message digest, it has a fixed size length. And so we're just assuming your digest output buffer is going to be at least the right length that we need. And looking at digest sizes, here's what the digest size is per algorithm in bytes. So it ranges, from MD4 is not really used much anymore. MD5 is becoming less used. SHA is 20 bytes up to SHA-2 and SHA-3 512, which is 64 bytes. If you need to copy the SHA structure, you can do that using our WC SHA copy function. That'll essentially, copy the entire structure over into a separate one that can then be used for its own operations. If you need to get the hash at any point in your application's flow without disrupting the internal state, because as soon as you call SHA final, that's going to finalize the SHA structure, and you can't go backwards and call update again on it. So if you want to just kind of get the hash in the middle and then continue on using that SHA structure, you can call WC SHA get hash. That'll return your digest. For usage reference and tests, we have functions in our wolfCrypt test.c for all of the message digests, following the same pattern of a SHA or message digest _ test in the naming. We've also got our Doxygen API reference, kind of one page or section per algorithm. For the other algorithms apart from SHA, they're going to follow the same pattern, having one header file per algorithm and one structure. In addition to using individual algorithms, we have a generic hash API. And so if you don't want to, have your API specific to an algorithm like SHA or SHA-256, you can use the more generic hash, init, hash update, hash final, where you're passing in a hash alg enum representing the algorithm type that you'd like to use. And we also have single shot APIs. So if you don't want to call init update final, you can just call a single API to do kind of all of those operations in one. If you just have a smaller chunk of data you want to pass in and get the digest out right away. Let's see. Okay, so next up is HMAC. This is a hash-based MAC, if you remember right. This is enabled by default with our configure. You can define it through C flags or preprocessor defines by defining no _ HMAC. And the underlying digests that are available to use are going to be dependent on what's compiled in. So essentially, you have all the wolfCrypt ones available under there, unless they've been compiled out or disabled. HMAC has one header file called hmac.h and one structure called HMAC. The first thing you're going to want to do when using HMAC is called HMAC set key. This does the initialization on the HMAC structure. And this is where you specify the type of HMAC that you're going to want to do as far as defining the underlying hash algorithm. And so options for the type are shown here. It's essentially a WC _ followed by a hash type. Then you pass in the key and the size in bytes of your key. Again, you can update as many times as you want with HMAC update, passing in more and more data. And when you're ready to get your final MAC out of it, you can call HMAC final. That value will be placed into your output buffer. There's some helper functions we have for use with HMAC. HMAC size by type will take in a type and return you the right output MAC size. There's also an HMAC get HMAC max size, which will return the maximum possible size of a MAC independent of, across all the message digests that are enabled underneath. Okay, so that gives you the quick overview of our message digests and HMAC. Next up, we're going on to block ciphers. So wolfCrypt has a number of block ciphers available for you. internally. We've got AES in a number of modes: ECB, CBC counter, CCM, GCM, CFB, OFP, and XTS. DES and triple DES in ECB and CBC mode, and Camellia in ECB and CBC mode. We're going to use our software crypto by default unless you have hardware crypto enabled at compile time. If you do end up enabling hardware crypto underneath wolfCrypt, in most cases, the higher level wolfCrypt APIs are going to remain the same. And we've already handled integration for you underneath those APIs down to the hardware. If we look at AES first, these are the enable options that we have available for you. We have one general enable AES, and then we've got enable options per mode. So you can see here, enable AES CBC, for example, enables CBC mode. Here you can see in the second column, the corresponding preprocessor define. All of these are kind of the positive enable options. We don't have any, I guess no AES is the only negative, which would be enabled by default. We have one AES header, AES.h, and one AES structure called AES. You'll want to initialize your AES structure with AES init. You can pass in again the heap pointer and dev ID if needed, and then free that structure with AES free. To go on, after you initialize the structure, you'll want to set your key and IV. We have AES set key to pass in the key of length, as well as an IV and a direction. If you are not passing in the IV initially, you can call the separate AES set IV function, or the IV should be the block size of AES. If you're using AES direct or ECB mode, we have a separate set of APIs for that. For setting the key for direct mode, there's AES set key direct. Just at the bottom, noting that the IV should be the block size of AES, which is 16 bytes. And the key length is one of our supported AES lengths, either 128, 192, or 256 bits, which translates into 16, 24, or 32 bytes. To encrypt data using AES ECB in direct mode, call AES encrypt direct. And to decrypt, you would call AES decrypt direct. Pretty simple and straightforward, passing in your AES structure, the output buffer that'll either be the encrypted output or the decrypted plaintext. And then the input, which would either be your incoming plaintext or your incoming ciphertext. If you're using AES CBC, similar functions, but now the naming is AES CBC encrypt and CBC decrypt with the same type of arguments there. The difference there compared to the direct ones is that now you have a size argument. Since encrypt direct and decrypt direct will be working on one block of 16 bytes, whereas AES CBC now you can specify a length that would likely be larger than one block. Other modes of AES have similar APIs. The naming is going to reflect the mode. For example, AES OFB has that in its API name of AES OFB encrypt and decrypt. Some of the AES modes are going to have different arguments depending on what the mode requires. For AES GCM, that's a mode you're going to notice has a number more of arguments than just the direct or CBC mode does. If you remember AES, well, GCM is a AEAD algorithm, so you have an authentication tag that's being generated or verified. So here you bring into the mix the auth tag and auth-in arguments, where auth tag is the authentication tag and auth-in is the authenticated data. If you remember that some data you can pass into AEADs, which isn't encrypted, but it's authenticated and becomes part of the authentication tag, that would be the purpose of the auth-in. So a special case of AES GCM is known as GMAC. This is where the plaintext is 0 or null, and only authenticated data is used to generate an auth tag. So we do have a separate API set for GMAC. You can see we have a GMAC set key, GMAC update, one GMAC function if you'd like to set the key and IV all in one go, and then a GMAC verify function to verify the authentication tag. So here's all the AES modes available in wolfCrypt. We have ECB, which is electronic codebook, also known as direct mode. CBC, which is cipher block chaining. CTR counter. CCM is counter with cipher block chaining. Message authentication code. GCM is Galois counter mode. CFB is cipher feedback. OFP is output feedback. And XTS is XEX, which stands for exclusive OR, encrypt exclusive OR based tweaked codebook mode with ciphertext stealing. For usage reference and test cases, we have an AES test function in wolfCrypt We've also got our Doxygen API documentation. For DES and triple DES, we support these inside of wolfCrypt. We only have one enable option for enable DES 3. The defines they're going to be no DES 3 if you want to disable that, or wolfSSL DES ECB to enable ECB direct mode. If you're using configure, this is disabled by default. Triple DES, the 3 in there essentially means that you're applying the DES cipher 3 times to each block. DES itself is considered insecure, and triple DES is a weak cipher, which is why we have it disabled by default. If you're going to use it, we have the DES3.h header and 2 structures, one for DES and one for triple DES, which is the structure name is DES3. We have an initialization function for DES3 init, a free function, DES3 free. And for triple DES, these are only required when you're using our static memory build or our asynchronous build. Otherwise, you can use them and they'll just essentially be a no-op internally. You can set the key and IV separately for DES and triple DES using these APIs. Again, the IV should be the size of the block length, which for DES is 8 bytes. The key length is either 8, which is for DES, represented by the DES key size, define or enum, and triple DES key size is 24 bytes. So these are the APIs you'd use for encryption and decryption. There's a DES ECB encrypt and DES3 ECB encrypt. In these functions, you're going to use the same, in these algorithms, I should say, for ECB, DES and triple DES, you'll be using the same API to decrypt as well. For CBC mode, you have separate encrypt and decrypt APIs, like you can see on the bottom of the slide here. Camellia, this is another block cipher we have available. This was originally developed by Mitsubishi Electric and NTT as kind of a joint effort in Japan in 2000. This is disabled by default in wolfCrypt, can be enabled by using enable-camellia or defining have_camellia. There's one header for Camellia called camellia.h and one structure called Camellia. You can set the Camellia key with Camellia set key and the Camellia IV with Camellia set IV. Here your IV should be the block size for Camellia, which is 16 bytes, and the key size should be either 16, 24, or 32. For Camellia ECB or direct mode, we've got a couple APIs you can see at the top here, and then Camellia CBC encrypt and decrypt here at the bottom. So that takes us through our block ciphers overview. Next up, we have digital signature algorithms. So we've got several digital signature algorithm options for you inside of wolfCrypt. We have RSA, DSA, ECDSA, and EDDSA. We've covered RSA, stands for Rivas Shamir Adelman, and has been around for the longest. Key sizes are 1024, 2048, 3072, and upwards. We don't see a lot of key sizes higher than 4096 being used yet. There's been a couple higher than that, but not many that I've seen. DSA stands for digital signature algorithm. It's not as widely supported or as popular as some of these other algorithms are. ECDSA is probably one of the most popular today, just because of the smaller key sizes of the same security level. Comparing, a 3072-bit RSA key in security level is equivalent to a 256-bit ECC key. So that's like a good amount of memory you can save, which is valuable on your embedded resource-constrained devices. EDDSA stands for Edwards Curve Digital Signature Algorithm. This is the newest one of the four here, invented and specified by Daniel Bernstein in 2011. There's a 256-bit version, which is ED 25519, and a 456-bit version, which is ED 448. So these digital signature algorithms use asymmetric crypto, meaning you have a public and private key pair that you're using for operations. Keys can be in different formats, encoded differently. Some of the encoding formats you'll see are PEM, which stands for Privacy Enhanced Mail, or DIR, which stands for Distinguished Encoding Rules. PEM is more of a base 64 encoded format, or usually a file, and DIR is more of a binary representation. So inside of our support for digital signature algorithms, we have APIs for key generation, signature generation, and verification, and then key export of either the public or private or both. Common use cases for digital signatures, vary. Typically, you're going to be signing a digest, though, instead of just signing your input data. Since some of them have limits. For example, RSA can sign up to its key size, whereas the data you might be wanting to sign might be much larger than that. So you'd make a digest of your data first and then sign your digest to generate your signature. So if we look at RSA first, we have 4 enable options for this inside a configure. For the algorithm, enabling public only or verify only options, and then enabling RSA PSS mode. You can see what's enabled and disabled by default on the right-hand column. The signature size of RSA is essentially the size of your key. So 1024 or 2048-bit keys will have a respective size signature. Using RSA from an application, you have one RSA.h header and one RSA key structure. Our RSA API is a little bit more extensive, I guess I would say, than some of the other algorithms are. So after we get through these slides, we can go ahead and walk through, just take a quick look at RSA.h and see what that looks like. There's different padding methods when you're creating RSA signatures. There's a PKCS #1 version 1.5. That's our default padding scheme. There's OAEP, which stands for optimal asymmetric encryption padding. And there's PSS, which stands for probabilistic signature scheme. For usage reference, in test.c, we have RSA test as a function, and then we also have our Doxygen API for RSA. For DSA, we've got one enable option, enable DSA, a define, which is the corresponding way to do it through C flags or preprocessor defines, and this is disabled by default. The DSA signature size is 40 bytes. From usage from an application, you'll include one DSA.h header. We have one DSA key structure, and we can also look at DSA.h as well. DSA test in test.c is where you'd look here for tests and usage reference, and the corresponding Doxygen API group. For ECDSA, here we've got 5 enable options for you. Enable ECC, enable ECC min size, which sets the minimum ECC size key that can be used. Enable FPECC, which enables a fixed point cache. ECC Shamir is an optimization for inside of ECC, and enable ECC cust curves enables support for custom ECC curves to be used with the library. The signature size for ECDSA is variable. It's going to depend on your curve that you're using. For example, the P256 curve, the max signature size there is 74 bytes. Usage from an application, you'll include ECC.h. And we have one structure, which is a little bit different, has an underscore in it. from the previous ones, ECC key. And we can look at the ECDSA API as well in ECC.h. So along with ECC, you're going to be specifying a specific curve that you're going to operate on. So these are the curves that wolfCrypt supports across the NIST prime curves, the SECP curves, the Kolblitz curves, and the Brainfill curves. In addition to these, if you have your own custom ECC curve, that's what the enable ECC cust curves option allows you to use. Usage reference and tests are located in ECC test of test.c with our corresponding Doxygen API docs available as well. And then lastly, our EdDSA. We have an enable option for Ed 255.19 and 448. Both of these are disabled by default. The Ed 255.19 signature size is 64 bytes. Internally, Ed 255.19 uses SHA-2512 and CURP 255.19. Ed 448 signature size is 114 bytes, where Ed 448 uses Shake 256 and CURP 448. wolfCrypt has two headers for these, the Ed 255.19.h and Ed 448.h. Two key structures, Ed 255.19 underscore key and 448 underscore key. Again, this API is a little bit more comprehensive. One thing to note here is that there's different variants of these algorithms. So the Ed 255.19 itself is the original algorithm. The message is hashed twice with different prefixes. It turns out it's difficult for hardware crypto to do since the entire message is, you have to send it in twice to be hashed. Because of that, there's some different variants that emerged. Ed 255.19ph was standardized in RFC 8032, which does a SHA-512 operation first. And then Ed 255.19ctx as a context, which is prepended to the hash data. So I guess there's use cases for those in different scenarios. And the similar in Ed 448 that has the original algorithm and then Ed 448ph. Again, you have two test cases in test.c, one function for each of these and corresponding Doxygen API. And that's the end of those slides. I mentioned we'll look through some of the headers real quick to give you an idea there. So let me switch over to my terminal window. So each of these headers is under the wolfSSL/wolfCrypt directory. If we look at RSA.h, it's a decent sized file, 450 lines. Let's see if we scroll down here. You've got some types and enums up front. You've got your RSA key structure. Here we can see you've got some similar functions for initializing a key and freeing it. Init RSA key looks probably fairly similar, where you can put a heap pointer in and dev ID pointer. Some helper APIs to check the RSA key for validity. Common ones you'll use are RSA SSL sign, which does an SSL sign, and RSA SSL verify. You have functions to do PSS signing and verifying if you'd like. And then the inverse operations of the RSA SSL sign is a RSA public encrypt and a RSA private decrypt. And so we've got APIs in here for those inverse operations as well. Some helper functions to check padding, to get the output size of the RSA operation, RSA encrypt size. Some key conversion functions. Sometimes it's helpful to be able to convert an RSA key to a dir array or vice versa. There's also functions to export the key as either components or a couple different formats. If we look at our ECC.h, we're going to see some similar trends. We've got enums up front, structures. You'll see use of the ECC curves we saw in the slides. Let's see if we can just jump to. And when you're looking through the header file, anything you see that says wolfSSL _ API, that's going to be a public function. If you see wolfSSL _ ABI, that's part of our ABI safe layer. And so those functions, we have some customers that want to do binary releases of wolfSSL from release to release. If you're using functions inside of this ABI safe layer, that's safe to do. It essentially means we're guaranteeing the ABI compatibility of these APIs going forward into the future. So we also have, there's key generation functions for all these algorithms too, which you'll find here in the headers. Here's doing an ECDH operation with ECC shared secret. Here's the sign function for ECC is called ECC sign hash. The verify operation is ECC verify hash. Some common init and free functions like we've seen trending with other algorithms. And then some other helper functions around curves and again, importing and exporting keys and in different formats. We have the DSA.h header. It's going to be very similar. Here you've got DSA, init DSA key and free, DSA sign and verify, as well as some functions to decode keys from arrays or from byte arrays into structures and vice versa. Some key generation functions and some import and export functions. If you want to use the ed, I mentioned they're in 255.19.h and 448.h. Again, they'll be very similar in format, giving you sign and verify functions, key generation functions, import and export functions as well. So depending on which APIs you need, it'll be kind of specific to what your use case is. All right, so we're going to move on to our next category of key agreement algorithms. We provide 4 algorithms under the category of key agreement: ECDH, DH, curve 255.19, and curve 448. We've covered, kind of what they mean: elliptic curve Diffie-Hellman, Diffie-Hellman. Curve 255.19 is a fast ECC curve, as well as curve 448. Key agreement algorithms, like we covered earlier, allow your 2 parties to independently generate a shared secret without actually having to send that secret itself to the other party. So this is used inside of TLS as well as other protocols as well. It uses asymmetric cryptography, where both of the parties have a public key and a private key pair. During the exchange, the public key is sent to the other side, which will then be used to generate the shared secret. Since ECDH is still categorized under ECC, you're going to be using the same set of ECC build options that we saw on our previous slide. You're going to be using the same ECC.h header and the same ECC key structure. You'll just get a couple different APIs to do a shared secret operation instead of a signing or verifying operation. So after you set up your key, you can generate a shared secret, which will actually take in 2 ECC key structures. As you see, you're taking in a private key and a public key. The private key would be the party that's generating this right here. The public key would have been received from the other party or peer. And then it generates the shared secret, placing it into out with a outlen, specifying the size of the output buffer coming in and then the size of the shared secret generated going out. You can generate a shared secret from an ECC key and an ECC point instead of 2 ECC key structures by using the extended EX function. Usage reference is in our wolfCrypt test under the ECC test function. For Diffie-Hellman, we have a couple enable options: enable DH and enable DH default params. We have enable DH enabled by default and the default params disabled by default. You'll include one header, dh.h, and one key structure called dh key. After you've set up your DH key structure, you have essentially one function to generate the Diffie-Hellman shared secret called DH agree. For test cases and in usage reference, you'll look at the DH test function with Doxygen API available as well. And then lastly, for the curve algorithms, 255.19 and 448, we have two enable options for you, as well as the corresponding defines. Both are disabled by default. One header per algorithm, one structure per algorithm representing its name. Then you have a similar shared secret API that takes in two curve 255.19 key structures or curve 448 key structures. You have an extended function, which you can specify the endianness if needed. Algorithm usage and reference is in the curve 255.19 and 448 test functions of test.c. So that gives you the overview of our key agreement algorithms. Next up is password-based key derivation functions. So these are used, as their name suggests, to take in a password, usually from a user, and then expand that out into a key to be used for later algorithms. We provide a couple different password-based key derivation functions in wolfCrypt. We have PKCS number 5, PBKDF. PBKDF is the acronym password-based key derivation function. This one applies MD2, MD5, or SHA-1 to generate keys. Its max key length is bounded by the size of a SHA-1 digest, which is 20 bytes or 160 bits. And this is really only recommended for compatibility with older legacy applications or systems. The PKCS5 specification has a second password-based key derivation function called PBKDF2. This applies a pseudo-random function to generate keys. The max key length is now unbounded instead of being the size of SHA-1. PKCS12 has a key derivation function that is also called PBKDF, defined in that specification. And then there's one called sCrypt. It was created by a guy named Colin Percival, originally for the TAR-SNAP online backup service. And so this is designed to be purposefully use more memory and resources to make it harder to attack with larger computer systems or adversaries. So first up is the PKCS5 PBKDF. We have one enable option, PWD based, which will group several of these together into that one enable option. You have one header to use, PWD based.h. It has no structures, which is different than the algorithms we've seen in the past. Just a function to use, WCPBKDF1. Here you can see it has an output buffer to store the generated key, password, which is an input of associated length, plen. Salt is an input to be used for the key derivation process. Length of that is denoted by slen. There's an iterations, which you can specify to denote the number of key derivation function iterations. And there's different specifications have different recommendations for the number of iterations to use. Klen is the desired length of your output key. For this one, it's bounded by your hash type. And then the hash type is represented by type H in the signature there. In wolfCrypt test, there's a function called PBKDF1 test and associated documentation. For PKCS5's PBKDF2, it uses the same configure option, enable PWD based. This is the one that uses a random pseudo function to generate keys. Same header file, no structures. The function here is WC_PBKDF2. Very similar arguments that you saw in the last API output for the key generated, a password coming in of length plen, a salt coming in of slen. iterations for the KDF, the key length you desire to output, and the hash algorithm to use internally. PBKDF2 test is in test.c with Doxygen APIs. The PKCS12 PBKDF is again under the same configure option. This implements the KDF described in RFC 7292 Appendix B and works with any supported HMAC function in wolfCrypt. Same header file and no structures available, just one API to use. Very similar again. Difference is, I guess, we have the purpose argument, which is an identifier that's supposed to indicate the purpose of the key. You can choose 1, 2, or 3 if the key should be used for encryption decryption, 2 if it's IV, an IV for encryption decryption, or 3 if it's used for a MAC. You have PKCS12 test and test.c for usage reference and tests. And then lastly, script. This is the one that does have its own enable option, enable script, which is disabled by default. This one's used as a proof of work scheme in some of the cryptocurrencies. For example, Litecoin uses script. It's defined in RFC 7914. We have one header available for you, pwd-base.h. No structures again, just one API called wc_script. Here we've got similar beginning arguments: output, password length, salt length. There's a cost argument coming in here, which represents the CPU and memory cost, which is essentially the iteration count used internally is 2 to the power of the cost. The block size is another new argument as compared to the other ones. Is the number of 128 byte octets in a working block. Parallel is the number of parallel mix operations to perform, and DK line is the length of the derived key. Just as a note on the bottom there, the memory required for script is calculated by the function 128 bytes times cost times the block factor. So if you used 128 bytes times a cost of 16,384 with a block factor of 8, would use 16 megabytes of memory. There's an EX function as well that uses iterations instead of the cost argument. You have one function in test.c, and this one we actually don't have Doxygen API that I saw for, but we'll have that coming down the line here soon. So that gives you an overview of our password-based key derivation functions inside of wolfCrypt. Up next, we'll take a look at PKCS7 and CMS. So CMS stands for cryptographic message syntax. These are essentially algorithms that allow you to encapsulate data in different ways. They support adding digital signatures on, they support encryption, and you can build them up kind of like an onion, where you can have some data types inside of other data types. You can attach attributes to them, either if you're using assigned data, it can be signed. And it's used in some other protocols. One example is SCEP, which is a simpler certificate enrollment protocol. Heavily uses PKCS7 or CMS for transport of the certificates and CSRs. If we look at the evolution of CMS, PKCS7 was the original version developed by RSA in 1993. Version 1.5 was the first version specified in RFC 2315. The IETF took over responsibility of PKCS7 and came out with RFC 2630 in 1999. And then that was updated to RFC 5652 in 2009. So CMS defines 6 content types: data, signed data, envelope data, digested data, encrypted data, and authenticated data. And all these have a slightly different use case depending on where you're planning on implementing this. The data type is essentially meant to wrap any kind of arbitrary data or octet strings. The interpretation of what goes into the data and is encapsulated really is left up to you as the application author. You could have internal ASN1 encoding inside of the payload if you need to encode something specifically for your application. SMIME uses this content type is one example. They encode MIME encoded content. Generally, from what we've seen, this is encapsulated in a different data type. So that might be data, signed data, envelope data, encrypted data, authenticated data that have a data type inside of them. The second type is signed data. So this consists of some content attached with one or more signature values to it. You can have anywhere from 1+ signers of the content, and each signer info gets attached to that bundle. Some typical applications of this are one signer digital signature on a data content type. So just providing a signature over some kind of data. Also, as used in SCEP, this is commonly used to transfer certificates or CRLs between parties. So the process to construct a signed data type, for each signer, you first calculate a message digest on the content. Each message digest is then signed using that signer's key, their private key. The signature and the information about the signer is collected into what they call a signer info structure to be appended onto that structure. So any certificates or CRLs can be embedded into the data type, and then all of that's packed up into what's called a signed data structure. This is what the RFC is showing you here is the structure of assigned data. You can see it has a version, digest algorithm identifiers, encapsulated content info, optional certificates, optional CRLs, and then signer infos, which include signatures at the bottom. The next type is envelope data. So this is literally, you can think of it as a digital envelope for one or more recipients to receive. A digital envelope is encrypted, and the content type can vary of that encrypted data. And then it includes the encrypted content encryption key. So the receiving party can decrypt the key to decrypt the content. The typical application we've seen of this is where you're enveloping either data or signed data content types. The construction process for an envelope data, you first generate a content encryption key. That content encryption key is encrypted then for each recipient so that they can decrypt it on the receiving end. The encrypted content encryption key and some other info are packed into what they call a recipient info structure. The content's actually encrypted then with that generated key, and the recipient info structures are collected up and packed into an envelope data structure. So you can see this one's a little bit more in depth. It also changes slightly if you're using RSA or ECC. Digested data is the next type. So this is essentially just data and a message digest of the data, typically used to provide content integrity. And it usually becomes an input to something else again. So maybe it might go into envelope data as the content there. The process to construct a digested data, you compute the digest on the content, and then the message digest algorithm digest and the content are all collected up into a digested data structure, which looks something like this. Encrypted data is what its name kind of denotes. It's essentially encrypted content of any type. It has no recipients and it has no content encryption keys. So your keys must be pre-distributed to the endpoint. Typical application is encrypting data just for local storage, where you might be using a PBKDF, password-based key derivation function, to derive the key from a password. The structure is a lot smaller, as you can see here. And then I think this is our last data type, authenticated data. It consists of content of any type, a message authentication code, and encrypted authentication keys for the recipients. So it allows recipients to verify the integrity of the content using the message authentication code. The construction process here is a MAC is generated at random. The MAC key is encrypted then for each recipient. The encrypted key in the recipient is collected into a recipient info structure. the MAC's computed on the content, and then the MAC, the encrypted key, and the recipient info are all packed up into an authenticated data structure. That looks something like this. And all of these things are ASN1 encoded to be sent over the wire. So we can look at just a quick look at a few bundles of PKCS7 CMS. So if we compile wolfSSL, let's enable PKCS7. PKCS7 output test bundles is a define we can use to make wolfCrypt test output its test bundles that it's using. So we'll wait for the library to recompile here. And we'll recompile with make. We'll run the wolfCrypt test with wolfCrypt test wolfCrypt. You can see we have some PKCS7 tests that passed, but if we look in the directory, we'll see a bunch of PKCS7 files have been generated. And so I'm just going to pick one out here to inspect. Let's just do this signed data using RSA and SHA-256. What I typically like to do is there's an application called dump ASN1. You can provide it a dir ASN1 encoded input file, and it'll dump out the ASN1 encoded in more of a readable format. So here you can see if we start at the top, we're not going to go through this whole thing, but you can see this is a signed data structure using SHA-256. Here's the internal data, right? That is really just encapsulating the string hello world. This is some information about the signer certificate. And then we get down to the bottom here. We have some attributes which can be attached for message type, content type, signing time, sender nonce, message digest. Then here's our actual signature down at the bottom, which is using RSA, SHA-256 with RSA. There's also a way to use the OpenSSL CMS command. Let's see if I have, might not have CMS on the Mac. Some versions of OpenSSL don't have the CMS command available. Anyway, if you did that, you would do something like OpenSSL CMS inform dir in your file name, CMS out and print. And then it decodes it a little better where you can actually see the signer info. It calls out some of this PKCS7 CMS sections a little more clear than just the raw ASN1. Okay, so up next, let's see. Time is 1:54. FIPS. So let's get started with wolfCrypt FIPS. FIPS is only applicable to some people, and some of you might not be familiar with it. It is kind of one of the big reasons people choose to migrate over to wolfCrypt. A certain set of consumers from OpenSSL. So this slide deck will clear up what it is, what we have to offer, and what's available. So, FIPS and CMVP and CAVP are all kind of tied back to NIST. You likely know what NIST is. If you don't, it's the National Institute of Standards and Technology here in the US. They implement essentially guidance for cybersecurity and privacy requirements. They issue standards and guidance for best practices. And really their goal is to facilitate adoption of strong cybersecurity capabilities. The CMVP stands for the Cryptographic Module Validation Program. This was established in coordination between NIST and the Communications Security Establishment of Canada, or CSEC. The CMVP promotes the use of validated cryptographic modules. And you'll see here, we're going to validated here is going to mean FIPS terminology. They enforce security metrics, and they also govern third-party labs called CST labs, cryptographic and security testing labs, where each lab takes the responsibility to verify a module. If a module meets a certain set of requirements, they coordinate with the CMVP during the validation process, and each lab reviews the submission from vendors and submits to the CMVP and helps coordinate the certificate. So why would you be interested in a FIPS 140-2 or 140-3 validated library? And when we say library here, we're referring to a cryptography library like wolfCrypt. Essentially, it's a checkbox item for a lot of DoD or government projects in the US. Some federal agencies purchasing crypto systems are required to have a FIPS validation for the crypto. And a validation is associated with a certificate. So you can go on the NIST site and actually look at a list of FIPS certificates. You could look up and find wolfCrypt on there or any number of other vendors. Also, in addition to just it being a checkbox item, a lot of organizations just at the regular private commercial level perceive an advantage to using a validated library, just to know that it's gone through the more extensive testing at the crypto level than a non-validated one has. So we do have a FIPS validated version of wolfCrypt, and we draw the FIPS boundary just around the wolfCrypt, and actually just around a subset of wolfCrypt itself. It's independent of SSL and TLS, so all of the wolfSSL's TLS code is out of scope. And we've done that on purpose, so since most of our bugs and vulnerabilities are found outside of the crypto code itself, we can still have our customers update from release to release of wolfSSL and maintain the same validated crypto module internally. So we have a 140-2 certificate that we've had for a few years now. Number is 3389. As compared to our older certificate, it expanded algorithm support. So you can see the additional algorithms listed on the slide that it grouped in to this certificate. A lot of good stuff at the time. Also, included functionality for doing some kind of hardware crypto almost, for Intel ASM. Things like AES-NI and AVX 1 and 2 can be included in the FIPS validation boundary. We have a lot of OEs on our certificate. So if you're not familiar with an OE, it's a combination of an operating system version, a processor, and a platform. And then in addition, one thing that isn't listed here is just the version of wolfCrypt that it's coordinated with. So we have these 5 plus additional 50 OEs listed on our certificate now, ranging from normal Linux and Windows to the embedded level with OpenRTOS, Yocto, Simsys RTOS QNX, some on the mobile side with Android and iOS, and some on the server side too, with things like Windows 10 Enterprise. Now, doing a FIPS validation on an embedded device has some challenges. We have to port the default shared library entry point, which is used to automatically run a set of known answer tests in our wolfCrypt library. We have to run CAVP test vectors that we receive from our test lab through wolfCrypt. We have to fit the FIPS module into the memory of an embedded device, and then we have to port the library itself over to the target environment. When a FIPS library is first loaded, 2 things automatically happen. There's a power on integrity check, which is an HMAC SHA-256 over the object files within the boundary of wolfCrypt FIPS. And that guarantees that the object files haven't changed between compile time and runtime. We also run a set of known answer tests for all algorithms inside the boundary to make sure the algorithm is working correctly at runtime. For the default shared library entry point, we use on GCC the constructor attribute that you can see listed here in the middle, and that does need to be ported depending on the compiler being used. This is a visual diagram of the self-tests which run on startup. If they pass, the algorithm access is allowed from the application into the module. If they don't pass, then the module is put in an error state. This is the process we go through as part of an OE addition to a certificate. And so our FIPS lab, the CST lab, issues us test vectors for algorithms. And this is a set of request files, essentially one per algorithm type of test. Sometimes there's multiple tests per algorithm. And then the way we've designed our test harness, we have a host that can run on a regular engineer's development machine, and then an embedded agent harness that can be put down on an embedded device. Typically, that'll communicate over a serial link. It can go over different transport mediums if needed. The development machine host harness will be responsible for collecting up the algorithm results and packaging them into a response file, which then gets sent back to the test lab for review. Some challenges in the agent IoT device and the test harness being split in two is that there's no standard file IO on an embedded IoT device usually. Some of the test vectors are pretty large, so the harness has to chunk them up and run them in smaller pieces. And that the test harness being split between the agent and the host was the solution that we found that works pretty well for that. As we mentioned, IoT device memory constraints pose a challenge. There's some mitigations or things we can do to help with that. We can configure algorithms differently sometimes. Oftentimes we'll have a configuration that you can tune an algorithm to be slower in trade-off for a smaller size on disk. Sometimes you can configure memory usage differently. So you can configure between more stack use or more heap use. So we have some customers that want to use all stack, or some customers that want to use no stack and all heap. And so we have options that let you configure all that in different ways. And we'll go through that a little bit in a future slide deck as part of this training. We can also shrink the module boundary down if needed and not have all the algorithms and only do a subset of algorithms to help reduce the memory footprint. Platform details can be very diverse on embedded targets, a variety of RTOSs, tool chains, compilers, memory configurations, etc. And a lot of the abstractions that we have in wolfCrypt have really helped to help our customers apply wolfCrypt to these different platforms. So when we're doing a new validation, we have a couple options. We can add a new OE or operating environment. We can do a rebranding validation where we take our certificate and rebrand it under a customer's name. Or we can grow or shrink the module boundary as a little bit larger of an effort. The time frame for all these really depend on what we're seeing as far as wait times at the lab and the CMVP. When we submit a FIPS validation to NIST, we just get put in a queue with no associated timeline. So we can make some guesses, but don't get any hard numbers back from them. So as we go through this process, the first thing we do is CAVP testing and algorithm certificates. We define the cryptographic module boundary that the customer wants using their exact platform definition. We port and test our module and harness to the validation target. We request test vectors from our FIPS lab, run those vectors through the module, return them to the FIPS lab. And at that point, if everything goes smoothly, we're issued algorithm certificates from the CAVP. Those algorithm certificates are listed publicly on the NIST website and are used as an input into the CMVP or FIPS process. Here we move on to step 2 to get the actual FIPS certificate updated. We update our security policy with the new OE details. We have to go on site and test at our FIPS lab with the customer hardware. We have our FIPS lab submit the whole package to the CMVP and then wait for them to finish review. If everything goes as planned, we get back either a new certificate or an update to an existing certificate, and that gets placed on the CMVP website, can be viewed by the customer or any other person interested in looking at it. So we can rebrand wolfCrypt FIPS validations when possible, or if needed. We can reduce or expand the algorithm boundary. One example of reducing the algorithm boundary was on an OpenRTOS device. You could think of a format as kind of a smart watch, where it didn't have a lot of memory, and we had to reduce it down to just 3 algorithms: AES, HMAC, and SHA. So FIPS 140-3 is the next revision of 140-2. We did submit a certificate for 140-3 early last year. And now we're waiting, we're in review right now at the CMVP and waiting for that process to continue. If we look at the benefits of FIPS 140-3, some of the same benefits as before as far as beneficial to federal agencies and DoD. 140-3 modernizes the standard. So it's now based on ISO and IEC International. It's easier to stay up to date with the later wolfSSL releases, since now this validation will be based on a newer version of wolfCrypt. The newer standards have some stricter requirements that vendors need to meet when doing a validation. Potentially, customers that want to go to higher validation levels than level 1 is now possible. And an architectural change is now that the algorithm self-tests are conditional per algorithm. So before, in 140-2, all of the tests for all algorithms in the boundary needed to run up front. And now they only need to run conditionally per algorithm when that algorithm is first used. So this can reduce boot times, especially on embedded devices. And then just that last point, we can more easily pull in some PAA, or process for algorithm acceleration, that wasn't available with our previous certificate, now into this certificate. So taking advantage of some hardware crypto on customers' platforms. So our current certificate is in review at the CMVP. It expands algorithm boundary even further past our previous 140-2 certificate. It includes the key derivation for TLS and SSH in the boundary, adds RSA 3072-bit, 4096-bit, RSA PSS, HMAC shows SHA-3, AES OFB, and it also supports running as a kernel module if a customer needs to run wolfCrypt inside of kernel mode. And I guess, if a customer does need kernel mode, that can be added as an OE. The full wolfCrypt API is still directly callable from other kernel modules when using wolfCrypt FIPS. We support Linux 3, 4, and 5.x kernels. The Intel AES-NI and AVX2 accelerations are available for some of our algorithms. And if we, in general, we can do this, it'll work for those customers that need us in kernel mode. Now, if you're using wolfCrypt FIPS, that can have benefits to a larger ecosystem of products, not just wolfCrypt FIPS itself. And so that can work underneath all of our products, or most of our products, and then a lot of open source third-party packages using our supported ports, our upstreamed support. So if you need to use Nginx or WPA Supplicant or OpenSSH or Apache with a FIPS validated crypto module, you can do that with wolfCrypt FIPS underneath. We talked a little bit about the Wolf Engine product. So OpenSSL has an engine API that allows you to replace OpenSSL's crypto or add additional crypto in beside it using the engine framework. And so either wolfCrypt FIPS 140-2 or 140-3 can plug in as an engine underneath OpenSSL and kind of provide you a route to swap at the system level the cryptography out without recompiling OpenSSL or your applications. And so that can be potentially kind of an easy drop-in replacement for OpenSSL to meet a FIPS requirement or another requirement that you might need wolfCrypt underneath. So that wraps up our FIPS 140-2, 140-3 overview. Hopefully that gives you an idea of what it's about if you weren't familiar with it before, or a little bit more information on where we're at in our process if you are interested in that. The next section we are going to go over is talking about hardware cryptography and how that can be used underneath wolfCrypt and some of the advantages that you gain there. So the wolfCrypt has its own software cryptography, but we can optionally use a number of different hardware crypto modules underneath. We've got some out-of-the-box support for quite a few now, and we're always adding more every year. Benefits to using hardware crypto are performance. Typically, your performance will be 3 to 10 times faster on an embedded device than just using software. Your footprint size will be smaller by allowing you to compile out some of the software crypto. You'll have better randomness. Oftentimes, there's a TRNG available in hardware that you can use to seed our PRNG. And in the best case scenario, you also have key storage, secure key storage available in the hardware in the format of a secure enclave or a secure element or a TPM module. Are there any possible downsides? I guess there are a couple. Transparency might be considered one. Most of these modules from silicon vendors are closed source or closed design. And so it's harder to see, into how those crypto modules and algorithms are implemented. So there could be some concern around that depending on the vendor that you're looking at. And then driver code, a lot of times, well, I should say sometimes when you're using hardware crypto, you need an extra layer of driver code or a driver library that sits in between the hardware and wolfCrypt or wolfSSL. But typically, we see this as usually minor downsides, and the advantages outweigh them in footprint size and performance. Many of the vendors now are offering crypto in their hardware in silicon. Some of the ones that we see frequently are Microchip, Atmel, NXP, ST, but the list goes on. Most of them will have a TRNG. Most of them will have a set of hash functions. That might be MD5, SHA, SHA-2. Most of them will have block ciphers, DES, triple DES, and AES. And some of the newer ones, we're starting to see them coming out with, more and more having some public key algorithms accelerated, which is really nice to see, given that those are the most performance expensive operations inside of your TLS handshake. So what does wolfCrypt currently support? This is part of our list that we currently have support for. Some of these are on the desktop enterprise side, like Intel's AES-NI and their Quick Assist. But a lot of them are on the embedded side from NXP, ST, Microchip, TI, Nordic, Xilinx, Renesas, or Cypress. For Intel, we support their AES-NI for AES operations, AVX1 and 2 for SHA accelerations, RD-RAND, and RD-SEED. We support their Quick Assist technology, which is an accelerator card for RSA, ECC, AES, SHA, HMAC, and MD5. From NXP, previously Freescale, we support the Coldfire SEC, Kinetis MMCAU, the NXP or LTC device, which is on the K82, 8182, ST Micro's STM32, a number of their platforms have crypto on board. The Cavium Nitrox, again, another accelerator card, which it does include RSA acceleration. Microchip Atmel, the MXMZ has some hash and bulk encryption acceleration. Their AT ECC 508A and 608A are accelerating ECC, which is interesting. Can also act as a secure element, storing some of those keys in the module. From TI, the TM4C 1294. We do support general ARMv8 assembly for AES and SHA. The Nordic NRF51 for AES and RNG. And what about performance? I mentioned we use our wolfCrypt benchmark a lot to compare performance software versus hardware. And so some of these numbers here have been gleaned from that. Here's a comparison of performance on the Microchip Atmel AT ECC 508A, doing ECC keygen, ECDH, shared secret generation, and then ECDSA sign and verify. So the first column there is just running with software crypto right on the SAMD21, which runs at 48 megahertz. It's a Cortex M0. The second column there is using the hardware crypto of the AT ECC device, and then that third column there shows you how many times faster it is to use a hardware crypto. So it ranges, from 6 to 24 times faster. This chart is a little bit blurry, but this is a comparison reference on STM32F217 software versus hardware crypto for some hash and symmetric ciphers. This one we actually saw earlier. This is the Kinetis K60 software versus hardware. So again, some algorithms perform, give you more advantage than others. So what about enabling hardware crypto? We try to make it easy. In wolfSSL, we typically try to just have one define per hardware crypto platform. Sometimes you'll need to compile in a few additional source files. If you're using configure and cross-compiling, that's probably, it may already be done for you. But if you're compiling it in your own IDE project, you might have to pull those in. And then on some of those platforms, you'll have to link against a hardware driver if that's required to access down into the device. So if we take an example, enabling hardware crypto for an STM32F4, you would define either STM32 RNG, STM32 crypto, or STM32 hash, depending on if you wanted, one, or you could define all these if you wanted the RNG enabled, the symmetric algorithms enabled, and the hash message digest enabled. You would need to compile in one additional source file, the wolfCrypt source port stm32.c, and then link against one of ST's hardware drivers, depending on your platform, either the STM32 CubeMX or their standard peripheral library. So inside of our wolfSSL directory, if you look under the wolfSSL wolfCrypt port directory, you'll see details about some of our other supported crypto platforms. And usually inside of this directory, you'll find a README with some more details specific to that hardware crypto, either in usage or in enablement. If you need, we can usually pretty easily add support for a new platform. It takes us, typically a week or 2 weeks, unless there's, more complexity on the driver side or more scope in terms of algorithms. All right, so that wraps up, a quick glimpse into hardware crypto, what we offer, how to kind of enable it, and where to look for more details. Next section we're going to talk about is moving up a little bit from direct cryptography and looking at X509 certificates and keys. And so we're starting to kind of bridge the gap up into, SSL and TLS and higher level protocols. So X509 is a standard for public key infrastructure. Some things that it specifies are how public key certificates should be encoded, certificate revocation lists, and also how the validation should be done of a certificate chain or certificate path. Certificates and keys are generally structured in ASN1 syntax, which is also kind of onion-like if you're trying to think of how it builds up. And we might look at that a little bit again here. This is the structure of an X509 version 3 certificate. So you're going to start out and have a version number, which will be 3 for version 3, a serial number of the certificate, the algorithm identifier, an issuer, so that's who has signed the certificate or issued it, the validity period, which starts with a not before date and goes to a not after date, the subject information, which is information about the peer represented in this certificate, subject public key information, including the algorithm, public key algorithm, and the subject public key. The issuer's unique identifier is optional, and subject unique identifier is optional. And then there's a list of optional extensions, which can also be included. At the end, you'll have the signature algorithm and also the signature itself that was applied to the certificate when signed by the issuer. You'll see a couple different encodings when you look at certificates. PEM we mentioned before was privacy enhanced electronic mail, which is a base 64 encoded version. If you open that up in a text editor, it'll look like something on the right side of the slide here, where you have a begin certificate at the top and an end certificate marker at the bottom. You'll also see .dir, .sur, .crt. Most of these are binary dir formats. If you opened them up in your text editor, it would just be binary data. Some other types you might come across are P7B or P7C. Those are PKCS7 formatted. We talked about that, if you remember, PKCS7 and CMS being a standard for signing and encrypting data. P12, which is a PKCS12 bundle, which can bundle together certs and private keys in one file. And .pfx, which was a predecessor to PKCS12. So a certificate chain is what you could probably guess being a list of certificates followed. So it has your server or peer certificate, followed by one or more intermediate CAs, followed lastly, by your root CA. The issuer of each certificate matches the subject of the next certificate. Each certificate in the chain is signed by the private key of the one before it. And the last cert in the chain is called the root CA. Typically, this is not sent as part of the TLS handshake, but you need to load that into your client or endpoint to correctly verify the certificate chain. So this is an example certificate chain at the bottom of google.com. So we can see Equifax Secure Certificate Authorities, the root CA, which signed the GeoTrust Global CA, which signed the Google Internet Authority G2, which finally signed Google's Leaf certificate for star.google.com. So how do we view a certificate in PEM or dir format? The easiest way to do this is using the OpenSSL X509 application. You can use the -in form option to specify either PEM or dir. You can use -in to specify the file name, -text to output a textual representation of the certificate, and -no-out just doesn't output the actual begin certificate and certificate data again. Okay, so let's look at a few certificates, and then we'll come back here. So I'm in wolfSSL. I'll go down into the certs directory. We have a lot of test certificates in here, so I'm just going to pick server ECC.pem. I'm going to use OpenSSL X509 inform PEM and server ECC.pem text no out. That gives us a nice textual representation of the certificate. We can see here it's version 3, serial number 3. Signature algorithm is ECDSA with SHA-256. This is our issuer information. It's not valid before December 16th of 2022, not valid after September 11th of 2025. There's our subject information, our subject public key info. So we know it's an ECC key, ECC public key, 256-bit. Here's our ECC public key. The curve it's on is the prime 256 v1 NIST curve. There's a few extensions here for subject key identifier, authority key identifier. It's not a CA, so you can say CCA is denoted as false. If this was a CA intermediate or root, that would be CA true. It has some key usage extensions here, meaning this we're denoting this certificate can be used for digital signatures, key encipherment, or key agreement. Some extended key usage is in here for TLS web server authentication. And lastly, here you see our signature at the bottom, which is ECDSA with SHA-256. So just as in comparison, I won't go through it all again, but just to show you a CA cert. Let's see. Let's look at just we'll look at a dir this time, caeccert.dir. So OpenSSL X509 inform dir in caeccert.dir text, no out. So this one, very similar structure. Now you can see our basic constraints does say CA is true. Okay, so you can use that same process to look at all kinds of certificates in either dir or PEM format. So what about generating keys on the command line? So typically, again, the easiest way is to use the OpenSSL tool, or you could potentially use the wolfClue command line utility as well. I documented the OpenSSL one here just since it's the most widely used. To generate an RSA key, we'd use the OpenSSL gen RSA command specifying the bits of 2048. We'd put that into a file. Here we're calling it cakey.pem. To generate an ECC key of 521 bits, we need to know the ECC curve name that we want to use. So we'll first use OpenSSL ECParam with list curves. That will list all the curves that OpenSSL supports. We can then run ECParam again with gen key -text -name with the curve that we picked, and then output that into a file. Here we're calling that ECC-key.pem. So that outputs a PEM encoded key, looks something like this. How about generating a cert? So we'll generate a CA cert using the OpenSSL rec or REQ application. We'll use -new -x509 nodes SHA. You can see we'll use SHA-1, specify it's valid for 1,000 days. The key we want to use is ca-key.pem, and we want to output this into ca-cert.pem. It'll ask us some questions about what we want to fill in as far as the subject information goes. So we can enter some data, hitting enter after each of these prompts. And it'll output a certificate that looks something like this into ca-cert.pem. Sometimes it's helpful to add the textual metadata into the file. And this would be the same data that we saw when we ran OpenSSL X509-text, but this is just a way you can put it into the file prepended on top of the actual certificate. So then you can open up the PEM file and actually see it in text instead of rerunning the X509 command. TLS library should ignore any text that comes before the begin certificate, and so it won't cause or shouldn't cause any problems. So now we'll generate a server certificate, OpenSSL rec. We're generating a new RSA key of 2048 bits using SHA-1, valid for 1,000 days. We're outputting our new key into server-key.pem. And then the output of this is going to be a CSR that we're outputting to server-rec.pem. So it's going to ask us some more questions, this time about the server we want issued here. That'll output, the request file to server.rec.pem. Now we need to sign that CSR by our CA certificate or our CA private key. So we'll do that using the OpenSSL X509 command. You can say we're inputting that CSR file, server-rec.pem. We want this new certificate file to be valid for 1,000 days using SHA-1. The CA that we'll be using is ca-cert.pem. The CA's key is ca-key.pem. We're going to set the serial number to 1 and output that into server-cert.pem. So if that all works correctly, we'll end up with a new server certificate file that looks like you would expect with base 64 encoded PEM format. We could look at that file using the command that we showed before, the X509-text, and see that it looks correct. So if you want to convert from PEM to dir, you can easily do that with OpenSSL's command line utility as well. Essentially just use, if you're doing a certificate, X509 inform PEM give it your certificate name, then do outform dir and give it a new output file name. And that'll just read it in PEM, output it in dir, and in a dir formatted file. You can also do the same thing with the OpenSSL RSA application using inform and outform. And you don't have to go always from PAM to dir. You can go from dir to PAM and vice versa. So what about if you're on an embedded device, you have a dir file, but your embedded device it does not have a file system. So you need to convert that file into a C array or a C buffer. So one option to do is to use our gen-certbuff.pl Perl script. If you wanted to use that, you would edit the script, add your certificate.dir into the script, run it, and then that would convert your file into a C array and place it in the certs_test.h header file. You could then include that header file in your application and go ahead and use that array like you would a certificate file. We also have another Perl script that is sometimes a little easier to use because it just accepts command line arguments. dir2c.pl, another Perl script. You essentially give it the path to a dir certificate, the name of the C array that you want it to output, and then the file that you want it to output that array into. So using this usage command, it'll be reading in a server-cert.dir, outputting it into an array called server_cert_dir_2048, and putting that array into a file called dir2c.c. You could then pull that out of the file and put it into your own application code. So there's some other X509 related topics you might come across. OCSP is Online Certificate Status Protocol. OCSP stapling is a version of that includes the OCSP result along with the certificate. And there's two versions of that, 1 and 2. CRL is a certificate revocation list, which is a file of revoked certificates for a specific CA. There's a number of X509 extensions, and then you're probably bound to encounter ASN encoding if you get down into too much depth with certificates and keys. We might, time permitting tomorrow, we'll go over a little more details on OCSP and CRL. Key management. Earlier in our day, we talked about the security of your crypto system depends on your private key security. So just since we were talking again about key generation, a reminder to keep your private keys private. And best case scenario, you can generate the private key on the device and it stays on the device. And just another, this is essentially echoing the same thing. You should use different keys for different functions, and your keys should change often. That matches your application's requirements to minimize vulnerability and exposure. I think we talked about key storage, ideally storing your keys down into TPM or HSM. So that kind of brings us to the end of our X509 certificates and keys presentation. Let's see what we have up next. So in that past slide deck, we were talking about generating keys and certificates on the command line. Now, if you're going to want to generate these, some people want to generate keys and certificates at runtime in your application. And so you can do that programmatically through our wolfCrypt API for either RSA or ECC keys, or some of our other algorithms too. So what this slide deck is going to go through what APIs you would use to generate keys and certificates using wolfCrypt. To enable key generation, you'll need a new configure option, -- enable keygen, or a define called wolfSSL _key_gen. And we'll start out with RSA key generation. So the key generation APIs for RSA are exposed in our wolfSSL wolfCrypt RSA.h header. Creating a key is pretty easy. It's essentially one API call, wc_make RSA key, where you pass in the RSA key, structure pointer, the size of the key you want to generate, the public exponent, and then a pointer to a wc_RNG structure to use for random data. the length, the size here is the length of the key in bits, and E, your public exponent is most commonly set as 65,537. You first need to initialize your RSA key structure using a init RSA key. Remember when you're done with it to free that key memory with free RSA key. Here's a little example of we're initializing our RNG structure, initializing our RSA key structure, and then generating a key of 1024 bits. The generated key would be inside of the RSA key structure. So then you can go on and use that structure, which is now holding a private key, which includes a public key, or you can use one of our export APIs to export that into a file or a buffer. If you do need to export that, say you want to convert the RSA key structure to a dir format, you can use WC RSA key to dir. That'll take in your structure pointer and give you essentially output into a provided array that you give as the second argument, with the size of that array being given as the third argument. It'll return the size of the generated dir or a negative value on error. Once you have that dir, if you need it in PEM format, we have an API WC dir to PEM, which takes in your dir array and converts that into a PEM array. And then the last argument there is either private key type if you're converting a private key, or cert type if you're converting a certificate. So the last function, RSA key to dir, exported the private RSA key. If you only want to export the public key to dir format, we have a separate API called RSA key to public dir, which takes an RSA key pointer and outputs the public key into a provided buffer. So now let's look at ECC key generation. So here you're going to use our ECC.h header again. We have one API just like RSA, but named slightly differently, WC ECC make key, which takes in a key size in bits and a pointer to an ECC key structure and an RNG structure. If you want, there's an extended version of this API which takes in a curve ID that will let you generate the key on your desired curve. If that's not provided, I believe it generates it on our default curve, which is NIST P256. The curve ID values come from the ECC underscore curve underscore ID enum, which is located in ECC.h. And again, you have options of all of our supported curves there. The curve ID will look something like this, depending on what curve you want. If you want to convert the ECC key structure, including both the private and public key components into a dir encoded array, you can do that using WC ECC key to dir. That'll take in the key structure, output that into a output array. If you want to convert the ECC key structure, only the private key into a dir format, you can use ECC private key to dir. And then if you only want to export the public component to dir format, you can use ECC public key to dir. That last public key to dir has a fourth argument, which is either true or false, depending if you want us to export the algorithm curve information prepended to the key or not. So you'd first need to initialize your ECC key structure. Again, a reminder, make sure you free the structure at the end of your use to avoid memory leaks in your application. If you want to check the key, if you want to check the ECC key structure to make sure it generated correctly, and this will do various checks mathematically and just some basic checks as well on the structure. You can call WC ECC check key API after your key generation. So now that you have a key, how do we go on and generate a certificate? So here we have a new header file that we haven't mentioned before. This is wolfSSL wolfCrypt ASN underscore public.h. Cert generation is off by default, but you can enable it with enable cert gen or defining wolfSSL underscore cert underscore gen. Before you generate a certificate, the user application needs to fill in a structure that we have, which is called cert. You can see some of the members here closely mapped to what we saw, in the certificate textual representation. There's a cert name structure that you can see represents the issuer and the subject, and that structure here has fields you would fill out for all of the cert name information like country, state, locality, etc. When we're generating the cert, we need to initialize the structure first with wc init cert. It sets some defaults for some of the values. When you're setting the signature type, it's going to look something like this, a CTC underscore. If you're wondering what CTC stands for, that stands for CTALcrypt, which is our old, wolfCrypt name. We just kept the same internal enum values around. So you'll set your signature value depending on what you desire there. This is an example of how you would initialize the subject information in the cert name structure. So setting the country, state, locality, organization, unit, common name, and email. If you want a full example of this, we do have one in our wolfCrypt test.c. We also have one in our wolfSSL-examples repository. That's just a smaller certificate generation example. Some other setter functions, if you want to set the subject key identifier from the public key, you can do so using the first API here. If you want to set the authority key identifier from the public key, you can do that with the second API. And then if you want to set the key usage, you can do that using the third API here. So let's first talk about making a self-signed certificate. So this is a certificate mostly used as a root CA that is signed by itself. So that's what happens when you go all the way up the chain. When you get to the top, the only option is it has to sign itself. Either used for testing or used as a root CA itself. We'll call the wc make self cert API. That'll take in your pointer to your cert structure that you filled out, output into an array called, here we're calling it dir cert. We specify the size of that array, a pointer to the key that we're using. That would either be an RSA key or an ECC key, and then a pointer to a WC RNG structure. So if this passes successfully, the buffer dir cert now contains a dir formatted certificate. If you need to convert from dir to PEM, you can use our wc dir to PEM API, just using that last argument as cert type to denote a certificate is being converted here. Now let's talk about creating a certificate that's CA signed instead of self-signed. So you need a couple extra steps. First, you have to set the issuer into your certificate structure by using the wc set issuer command. That second argument there is actually a path to a file, a CA file. If you don't want to use a file for the issuer, you can set that from a buffer, a dir buffer, using wc set issuer buffer. Now we need two steps. We have to create the certificate and then sign the certificate. So we create the certificate with make cert and then sign the certificate with sign cert. Before we were using make self cert, which does both of these in the same operation. So here we are calling wc make cert first of all, and then we're calling sign cert, specifying the certificate body size, the signature type, an output array, a pointer to the CA key that we're going to sign with, and then a pointer to an RNG structure. The output of this, if successful, is again a dir encoded certificate, but this time signed by the CA key that you specified into sign cert. Okay, so that wraps up key and certificate generation and how you do that via API. The next slide deck we have is, again, related to certificates, but this time is about what we call the wolfCrypt certificate manager. And so imagine you want to do standalone certificate verification programmatically. So if you have some CAs, you have some peer certs or some cert chains, and you want to verify them outside of the scope of TLS and just individually at the cert level. So yeah, this was designed to be used independent of SSL and TLS and DTLS. You can use it to load certificates, verify certificates, and also check the revocation status of certificates. The first thing you want to do is initialize a new cert manager structure. This is done by using wolfSSL cert manager new or wolfSSL cert manager new EX. Note here that now we've essentially moved up from the wolfCrypt level to the wolfSSL level. And that's why we've gone from the WC underscore prefix to now the wolfSSL underscore prefix in our API naming. If you want to pass in your own custom heap pointer, you can do that using the extended function. And then a reminder, make sure you free up your cert manager memory before you're finished to prevent a memory leak. So the first thing to do is to load in some CAs into your cert manager that you're going to use for verification. You can call cert manager, wolfSSL cert manager load CA with a path to a certificate, a CA certificate file, or just a directory path, and we'll load all the CAs in that directory. If you don't want to use files, you can call cert manager load CA buffer, which takes in a buffer in either dir or PEM format specified by the last argument there. So then when you're ready to verify a certificate, we have a cert manager verify API, which takes in the certificate that you're looking to verify. So the first one here is taking in a file path in either a dir or PEM format, again, specified by the last argument. If you don't want to work with files and you just want to work with memory buffers and arrays, that second API at the bottom is doing the same thing, verifying the certificate, but this time taking in a C array of size SC in the right format specified as the last argument. If you want to unload all your CAs that you loaded in from the cert manager, you can do so by calling wolfSSL cert manager unload CAs. Some consumers want to set a verify callback. So if verification fails when verifying that certificate, the verify callback will be called and allow you to do some extra inspection there on that certificate. You can see here, wolfSSL cert manager set verify takes in a cert manager pointer, structure pointer, and also a callback, verify callback. Verify callback is prototyped in our SSL.h header, and it looks like that the function signature on the bottom of the slide here. So when your callback is called, you will get the first argument will be called pre-verify, which indicates if wolfSSL has already verified that internally by the time you get to that callback. And then you'll get a wolfSSL X509 store CTX pointer that is pointing to the certificate store, which allows you to dig in a little bit more for certificate details. So CRL, certificate revocation lists. There we go. So these are files that have a list of revoked certificates per CA. So the cert manager can work with CRLs. You would need to enable CRLs by calling cert manager enable CRL. That can take some options at the end. I think right now we only accept one option, which is called wolfSSL CRL check all, which just indicates that you want to check all the certs in the chain against CRLs, not just the leaf server certificate. If you want to disable that at any point in runtime, you can call wolfSSL cert manager disable CRL. Once you have CRL support enabled in a cert manager structure, you need to load in the CRL file. So this is taking a path to a CRL file or a CRL directory. And then if you want us to monitor the directory and load in new files. If you don't want to use files, you can use a C array or buffer using the function on the bottom here. To check a certificate only against the CRL list and not do the full verification against the intermediate and root CAs, you can call cert manager check CRL, passing in the certificate that you want to check. as a dir. But otherwise, if you've already enabled CRL in the cert manager, it's already going to check CRLs as part of the normal verification process. So in that case, you wouldn't need to explicitly check the CRL again. We have a CRL callback. So if we try to check a peer certificate against CRL and we can't find the CRL that matches the CA that certificate has been signed by, we'll call this callback for a missing CRL and essentially give you a link or give you a URL that's included in the certificate that points towards where that CRL is at. Your application could optionally, go off and pull down the CRL from that URL if needed. So if we have a callback that allows you to fetch and download and then load that CRL, here you can register that callback by using cert manager set CRL _ IO CB, which is prototype of the CB CRL IO function signature in wolfSSL's SSL.h. In order to get access to this feature, you have to have the define have _ CRL _ IO defined. And then when you're all done, you can free up loaded CRLs if you want by calling cert manager free CRL. The next kind of certificate verification or validation check that you can enable is OCSP with cert manager. So this is online certificate status protocol. Again, we just have one API here which enables it. It takes a couple options. You have OCSP check all, it checks all the certs in the chain, just like CRL did. OCSP no nonce, which indicates to wolfCrypt don't send an OCSP nonce in the request. And then OCSP URL override. The user can provide an override responder URL instead of using the OCSP responder listed in the cert. You can disable OCSP if you need, just like we had an API to enable it. If you want to provide a custom or override the URL for the OCSP responder to use, you can set that using cert manager set OCSP override URL. If you do, you have to have passed in the option when you enabled OCSP that allows this functionality to happen with wolfSSL OCSP URL override. And then when we verify the OCSP, we'll use your custom URL instead of the one listed in the certificate. So we have another callback for OCSP, which we call the request callback. If you want to customize how the OCSP response is sent to the responder, you can register this callback and you'll get more control then over what's sent. So here's the API you can use to register that callback, and then the prototype that you would need to implement against. If you want to enable OCSP stapling, you can do so. So normal OCSP will go out and contact the OCSP responder and then come back. OCSP stapling staples the responder response to the certificate. So that kind of wraps up how you might use our certificate manager. It can be pretty useful depending on your needs, especially if you want to try to do that outside of just inside of your TLS connection.